Hello everyone, welcome to OM Institute. I am Surendra Reddy, faculty for electrical machines at OM Institute, Hyderabad. So very warm welcome to the series, GATE Champions series that we are conducting from past few days. In this GATE Champions series, the first lecture from electrical machines is single phase transformers. Okay. So as you know that this series we are conducting for free in YouTube through live lectures, and we will discuss the subject in a very crisp manner, that is a quick review on the subject. And in this session I am going to discuss about single phase transformers, so where I'll discuss all the topics related to single phase transformers. Okay, I'll introduce the concept to every topic. Okay, we will revise the important formulae, and we will also solve the relevant previous GATE questions so that you'll get complete understanding over the subject. Okay, so this particular session will be useful for those students who are looking for a quick revision of the subject. Okay, all right. So without wasting our time, let us move on to the topics that I am going to discuss in this particular lecture. Okay, so we will first discuss about the self and mutual induced EMFs. Okay, and then EMF equation of the transformer, and we will observe the transformer behavior at no load condition and also at loaded condition. Just a moment. Yes, we will observe the transformer behavior at no load condition as well as at loaded condition. Then we will talk about the equivalent circuit of a transformer and what are the various power losses in a transformer. So we'll also discuss about open circuit test, short circuit test, and efficiency calculations and voltage regulation calculations. Okay, so these are the topics that I am going to cover in this particular lecture. So I expect the lecture is going to be around 1.5 hours to 2 hours. Okay, in between, and hopefully you will learn the basics of single phase transformers, and you will also understand how to solve the relevant GATE examination questions. Okay, all right. So let us start with the basics. We all know that a transformer is a device which transfers electrical energy from one circuit to another circuit through mutual induction concept, right? Transformer will work based on mutual induction principle. Okay, and according to Faraday's law, we know whenever a coil is placed in any time varying magnetic field, it will experience changes in flux linkages so that an EMF will be induced across the coil, right? And what is the magnitude of that induced EMF? N d phi by dt, important formula, where N is nothing but the number of turns that we are using in the coil. And you can see here d phi by dt, this represents the change in flux with respect to time. That's why we need a time varying magnetic field. And how to create a time varying magnetic field? Very simple. You take a magnetic circuit, wound a winding on top of it, and excite that winding with AC supply so that time varying flux can be created. Because what is the formula for flux? Important. Flux is equal to MMF divided by reluctance of the magnetic circuit, where MMF is nothing but magnetomotive force, that is N into I divided by reluctance of the magnetic circuit. So where N is number of turns, and you can see current is the excitation current that we are giving. So if you give AC current here, that is a time varying current, automatically the flux is also going to become time varying flux. Whereas if you give DC flux here, the flux also becomes, DC current here, the flux becomes time invariant magnetic flux, that is DC flux. Okay, so for the purpose of transformer, we need time varying magnetic field. Therefore, we have to excite the magnetic system with AC current. All right, fine. Now the point is, according to Faraday's law, we can only know the magnitude of the induced EMF, which is N d phi by dt. But to identify the polarity of the induced EMF, we will use the help of Lenz's law. Okay, so as per Lenz's law, the induced EMF will be written as minus N d phi by dt. Okay, so we can go through this derivation, okay, in regular class, but in this quick review session, directly I am writing induced EMF is equal to minus N d phi by dt. So this minus sign is as per Lenz's law. Understand? So this is the EMF equation with polarity as well. And also, if you go through this equation, if you go through the derivation of this equation, you will understand that induced EMF will always lag the flux by 90 degrees. Okay, that means if you take flux phasor at an angle 0 degrees, then induced EMF phasor will lag that flux by exactly 90 degrees. Okay, you know, any phasor rotating in clockwise direction is a lagging phasor. Rotating in anti-clockwise direction, that is a leading phasor. Okay, so the induced EMF is at an angle minus 90 degrees because it is lagging the flux by 90 degrees. Okay, all right. Now we will try to understand what is meant by self-induced EMF and what is meant by mutual induced EMF. All right. So look at this. This is a typical single phase transformer. A transformer will have two windings. This is primary winding, which will be connected to the source, and this is the secondary winding, which will be connected to the load. But right now the load was not connected, so I can say transformer is under no load condition. Now we are exciting this primary winding from AC voltage source. That is important. Therefore, the current drawn by primary winding, this is also going to be AC current, alternating current. So when the current is alternating, automatically the flux that is going to be created is a time varying magnetic flux. So we know whenever current is passing through any winding, flux will be created. How to identify the direction of flux? Right hand thumb rule. According to right hand thumb rule, if the four fingers represents the current direction, then the thumb represents the flux direction. So this is how the flux is going to be created. And we call this flux as main flux. Also we can call it as mutual flux. Okay, so why the word mutual flux is used? Because this flux is linking both primary as well as secondary. But strictly speaking, in practical transformers, entire flux will not link both primary and secondary. Some amount of flux will be lost due to leakage. Okay, we will see later what is leakage flux, etc. Okay, but right now the flux is linking both primary and secondary, therefore it is a mutual flux. And whatever EMF is induced across the primary winding, this is what we call it as a self-induced EMF. The EMF that will be induced across the secondary, we call it as mutual induced EMF. Okay, so self-induced EMF means it is the EMF induced across a coil due to the time varying flux created by its own coil current. Okay, mutual EMF means it is the EMF induced across a coil due to a time varying flux produced by some other coil current, which is mutually coupled. Okay, so that is what self EMF and mutual EMF. Okay, now we will see what are the mathematical formulas also for self EMF and mutual EMF. Yes, self EMF is in the primary winding. Primary winding has N1 turns. Mutual EMF is across a secondary winding. Secondary winding, okay, it must be N2. Okay, actually, yes, secondary winding has N2 number of turns. Okay, so let us write down formulas now. Yes, self EMF is equal to minus N1 d phi by dt, where this phi is nothing but mutual flux. And why that minus? That we discussed already as per Lenz's law. Okay, yes, self EMF is minus N1 d phi by dt, and you can also write that formula as minus N d phi by dt can be written as minus L di by dt. Both are going to be equal. Minus N d phi by dt or minus L di by dt, where L is known as self-inductance of the coil. Okay, similarly, mutual EMF, which is induced on the secondary side of the transformer, can be written as minus N2 into d phi by dt. Remember, this d phi by dt and this d phi by dt both are absolutely same. Why? Because same flux is linking both primary as well as secondary. But only the number of turns are different. Self EMF is across N1 turns, but mutual EMF is across N2 turns. Okay, and you can also write this formula as minus N2 d phi by dt can also be written as minus M di by dt, where M is known as mutual inductance of the coil. Understand? Okay, mutual inductance between primary and secondary. Now there are formulas for this L and M also. So L is equal to N1 square by R. okay, where R is known as reluctance of the magnetic path, a very important quantity. And M, mutual inductance, M is equal to N1 N2 by R. Again, R is nothing but reluctance of the magnetic path. Okay, reluctance means it is the property of the magnetic medium which will oppose field flux. Okay, just like conductors will have resistance, right? Resistance is the property of a conductor which will oppose current flow. Similarly, reluctance is the property of magnetic medium which will oppose the field flux. Okay, just like resistance. So L is N1 square by R. As it is inductance, the unit is henries. Mutual inductance M is N1 N2 by R. Okay, N1 N2 by R. Now, what is the reluctance? What is the formula for reluctance? Okay, as I told you, the definition for reluctance, it is a property. It is a property of magnetic medium which will oppose the flow of a field flux. Now, what is the formula for reluctance? Yes, very important formula. Reluctance is equal to length of the core divided by mu into cross-sectional area, and it is ampere turns per Weber. So where LC is nothing but length of the core. You see, the flux is passing through core medium, right? The total length of this flux path is indirectly the length of the core medium. That is what we have to use here. And mu is known as permeability of the magnetic medium. Permeability. Okay. Permeability means it is the ability of the magnetic medium to allow flux through it. Suppose if I say this material has more permeability, that means more flux can pass through this medium. If I say this material has less permeability, that means a very less amount of flux can pass through that medium. And again, you can write mu is equal to mu naught into mu r, where mu naught is a fixed value, that is the permeability of air medium, 4 pi into 10 power minus 7, and mu r is known as relative permeability. Relative permeability, or we can also call it as per unit permeability. Any word you can use. And it is a unitless quantity, and this relative permeability will depend upon the medium that we are using. Are we using a steel medium or iron medium, or what type of medium we are using for the magnetic flux path? That will decide the relative permeability. Okay. And then cross-sectional area, the core cross-sectional area. Understand? So these three factors will decide the reluctance, and reluctance will decide self-inductance and mutual inductance both. Okay. Now we will try to answer one simple question related to this reluctance formula of a magnetic medium. Yes, this is a question in GATE 2018 for 2 marks. Okay, important model. Just to go through the problem. A transformer with toroidal magnetic core of permeability mu is shown in the figure. Assuming uniform flux density across the circular core cross section of radius small r, which is less than the capital R, and neglecting any leakage flux, what is the best estimate for the mean radius capital R is? So we have to find out the answer for this capital R value. And there are 4 options. You can understand all the options are in terms of permeability, voltage, resistance, number of turns we are using for the winding, okay, omega, that is the frequency, and voltage. Okay, various factors are there. So let us quickly understand. There are 2 windings on the transformer core. Primary winding has a NP number of turns. Secondary winding has NS number of turns. Okay, and you see, primary winding was connected across a voltage source. And what is the voltage source? Primary voltage is equal to V cos omega t. So, according to this equation, can I say this V is nothing but maximum voltage indirectly, coefficient of cos term. Therefore, the maximum voltage is equal to V. Okay, this is the first equation. Also, what is the current drawn by the transformer winding? It is given I sin omega t. Current drawn by primary winding is equal to I sin omega t. According to this equation, can I say that I is nothing but maximum current? So that is the maximum current I. So now you have a maximum voltage with you and maximum current with you. Using these two, I have to find out this capital R value in terms of the remaining parameters. Okay, so this is where I will try to use the reluctance formula. Okay, so how reluctance can help us? Most important thing is, you see the secondary was connected to any load or there was no load? There was no load. As there was no load, I must say this current is nothing but magnetizing current of the transformer. Magnetizing current means it is the current responsible to create flux in the transformer core. I will talk about it also in a separate slide, but you try to understand the no load current. This is nothing but magnetizing current. And that current will create flux in the transformer core. What is the formula for flux? Yes, we know flux is equal to MMF by reluctance, where MMF is nothing but N into I divided by reluctance. But right now this I is maximum current. As this I is maximum current, this phi is also going to be maximum flux. Okay, so therefore how many turns we are using? NP. Primary has NP number of turns into I divided by reluctance. Suppose if this I is RMS current, then this flux also becomes RMS value. But right now, according to current equation, this I is maximum current, so this flux is maximum flux. Now I will try to figure out reluctance value so that I will get flux information. What is the formula for reluctance? I already explained. Length by mu into cross-sectional area. What does mean by length here? Length means indirectly the length of the flux path. You see, flux is circulating like this. Okay, and what is the radius of this circle? Capital R. If the radius is capital R, what is the length of this circle? Is it not perimeter of the circle? 2 pi R. So therefore, the length of the core, just a moment. Okay, so the length of the core is equal to 2 pi into capital R. Okay, what is the cross-sectional area? You can see here, you can see this core has a thickness, a circular cross-section, and the radius of this circular cross-section was a small r. Okay, for a circular cross-section, radius is small r, then what is the area of cross-section? Is it not pi r square? Okay, so therefore, the radius of cross-section, or you can say cross-sectional area, is pi into small r square. Now you have a length and area so that we can find out reluctance. So the reluctance is equal to length of the core by mu into cross-sectional area. Length is equal to 2 pi into capital R by mu into cross-sectional area is pi r square. I think pi will cancel in a numerator and denominator. So the reluctance is 2 into capital R by mu into r square. Now can I substitute this reluctance in this flux formula? Therefore, what will be the flux value? If I proceed, yes, the flux is equal to number of turns in primary winding into maximum current I by what is the reluctance we got? 2 capital R by mu r square. 2 into capital R by mu into r square, that will go to the numerator. Okay, take it as equation number 3. I have maximum flux value. Now you see, you have already maximum voltage and we have a maximum flux also. So how can I write formula for voltage? Yes, we know according to Faraday's law, the induced EMF or voltage magnitude is equal to N d phi by dt only. Yes or not? Where N is nothing but number of turns, and how many number of turns are there? NP number of turns are there. NP into d by dt of, can I write phi is a time varying flux or time invariant flux? Remember, the current is sine omega t, sine term. Current is a sine term. If current is a sine term, can I say flux is also going to be a sine term only? Yes. So phi is phi m sine omega t. Okay. So if I complete the derivation, number of turns in primary, phi m I can take out of the derivation. What is a sine omega t derivation with respect to t? Is it not omega cos omega t? Okay, so this is the voltage magnitude expression. Now you tell me here, what is the coefficient of cos term? This value. Can I say this is nothing but maximum value of the voltage indirectly? So when I express voltage as Vm cos omega t, the coefficient of cos term, this is nothing but maximum voltage. Okay, so therefore indirectly maximum voltage will be equal to number of turns in primary into phi m into omega. But what is maximum voltage already? Is it not V only? Yes. So therefore V is equal to number of turns in primary into phi m. Phi m we have an expression, right? What is expression? NPI by 2 capital R mu R square. NPI by 2 capital R into mu R square into omega. So what is the answer finally we need? Finally, our requirement is to find out this capital R value. So let us separate that. So if I separate capital R from this equation, the numerator NP into NP, it becomes NP square, current I, mu, small r square, omega by 2 into V. So this is finally the expression for that radius capital R. Okay, now understand which option satisfies that. Okay, see square of the terms, square of the resistance. I think first option has, this is wrong because it is NP only, R square. Okay, next omega is there in the numerator. Also denominator 2V, right? Denominator 2V, this is wrong. Okay, this is wrong, this is correct. Okay, because here denominator I, here 2I, here V, but the denominator is actually 2V. Numerator you can check, mu is there, I, R square, NP square, omega. Okay, I, R square, NP square, omega, mu by 2V. That's all. So the last option is correct. So it's a 2 marks problem, guys. You can spend around 4 to 5 minutes to solve this particular question. Okay, so the moment you see the question, according to options, you need to decide in terms of what I have to derive the formula for this radius R. Okay, the moment you see the options, there is mu, okay, number of turns are there, small r is there. You have to understand, you must use a reluctance formula to derive that equation. Okay, yes. All right, let us try to answer one more question. This is another question. This is a question from GATE 2009 paper. Okay, so this is also a question related to the concept that we discussed, self and mutual induced EMF. Okay, let's see the problem. The circuit diagram shows a 2-winding lossless transformer with no leakage flux excited from a current source I of t whose waveform is shown below. Okay, this is a current waveform. You can see it's a triangular waveform. The transformer has a magnetizing inductance of 400 by pi millihenry. See, magnetizing inductance was given 400 by pi into 10 power minus 3 henries because it is millihenry. Now what is the first question we have to answer? What is the peak voltage across A and B? See, voltage across A and B and voltage across primary both are same. Why? Because it is a 1:1 ratio transformer. Okay, so can I say primary voltage and secondary voltage both are same, but you have to find secondary voltage, which is nothing but a mutual induced EMF. So we know mutual induced EMF is nothing but M di by dt. Only magnitude I am finding. You know, I told you already, mutual induced EMF, you can write M di by dt. And M value was already given in the problem. So you have to find out di by dt. Can I say di by dt is nothing but change in current with respect to time? Okay, look at the current waveform. For the triangular waveform, the peak value was a 10 ampere. So what is the change in current? If you look at the first 5 milliseconds, okay, first 5 milliseconds, current was changing from 0 to 10 within 5 milliseconds. So here di by dt is equal to the change in current 0 to 10, that is 10 ampere divided by within how much time? 0 to 5 milliseconds. 5 milliseconds. So it will be 2 into 10 power 3. Di by dt means ampere per second. And you substitute this di by dt in the above formula. Therefore, the mutual induced EMF is equal to M di by dt. What is M? 400 by pi into 10 power minus 3 into di by dt 2 into 10 power 3. So 10 power 3, 10 power minus 3 will cancel. Therefore, the magnitude of mutual induced EMF is 800 by pi volt. But the question is, they are asking peak voltage. To understand what is the peak voltage, first you should know what is the shape of this mutual induced EMF. Can I say the shape of mutual induced EMF, I can decide based on the formula. You see, mutual induced EMF is directly proportional to di by dt, where di by dt is derivative of the current with respect to time. What is the shape of the current here? Current is a triangular waveform, and you tell me what is the derivative of a triangular waveform? Is it not a square waveform? Therefore, the mutual induced EMF is simply a square waveform. And what is the magnitude of this square waveform? 800 by pi. Therefore, negative half cycle minus 800 by pi. So they are asking peak to peak voltage or just peak voltage? Just peak voltage. Therefore, the magnitude will be 800 by pi volt. I am only calculating magnitude of the voltage. So this is the answer for the first question. Next, you look at the second question. In the second question, current waveform was not given. Instead, current equation was given. This is the current equation, guys. What is the peak voltage across A and B? But important thing is, remember this current is passing through primary winding, but voltage you have to find on the secondary. That means once again, mutual EMF we have to calculate. So what is the formula for mutual EMF? Okay, this is M di by dt. So M is 400 by pi millihenry, that is 10 power minus 3, into di by dt, that is d by dt of current equation was given. How much? 10 sine 100 pi t. 10 sine 100 pi t. Is it looking like 10 sine omega t? Now you can take 10 outside. So 400 by pi into 10 power minus 3 into 10 was taken outside. Then what is the derivative of sine 100 pi t with respect to t? Is it not sine omega t derivation? What is sine omega t with respect to t? Omega cos omega t. So therefore this is 100 pi cos 100 pi t. Okay, so now pi will cancel. You see, 2 zeros 1 0, 3 zeros 10 power minus 3 will cancel. So finally answer is 400 cos 100 pi t. Is it like 400 cos omega t indirectly, where omega is equal to 100 pi? Now what is the answer they are asking? The peak voltage, again you see that they are not asking RMS voltage, they are asking peak voltage. What is the peak voltage of this cosinusoidal function? Therefore the peak voltage is equal to 400 volt. Suppose if they ask you what is RMS voltage of the output voltage across A and B, we know RMS value means it is maximum value divided by root 2 for a cosinusoidal waveform, correct? So then 400 by root 2 would have been the answer. Okay, so this is also a question related to, you know, self and mutual induced EMFs. Okay, simple. All right, now let us come to an important current component in a transformer, magnetizing current. I already explained what is meant by magnetizing current. It is the component of current drawn by the primary winding of a transformer to produce magnetic flux. So you take a simple example. Consider we have a transformer like this. Okay, so here we have the primary winding. Okay, let's say with the N1 turns, and here we have secondary winding with the N2 turns. Okay, now this primary winding I am connecting across an AC voltage source. The moment when secondary I am not connecting to any load, that means the transformer is under no load condition. Now see, the moment when you connect a voltage source, immediately this transformer will draw a current, and that current will create flux in the transformer. See, according to the direction of current, flux will be created. Okay, so now the point is the current which is responsible to create this flux, that is what we call it as magnetizing current. That is what I am talking about here. So magnetizing current means it is the current component that is responsible for the creation of a flux. Okay, and you can simply write formula flux is equal to mmf by reluctance. So MMF is nothing but N into I, and this I is what we call it as magnetizing current. Suppose if magnetizing current is 0, the flux also becomes 0. If magnetizing current increases, the flux will increase. Okay. Therefore, this current will represent the flux that is created in the transformer. So we call that current as magnetizing current. Okay. And some important properties we need to understand. Magnetizing current is a purely reactive component. It is a purely reactive component. Okay, purely reactive component, and it lags supply voltage by 90 degrees. It lags the supply voltage by 90 degrees. Understand? Okay. So magnetizing current is a purely reactive component, and it will lag the supply voltage by 90 degrees. And most importantly, magnetizing current is inversely proportional to permeability. That means the magnitude of the magnetizing current will depend upon the permeability of the magnetic core that we selected. And we know transformer is always designed using high permeability ferromagnetic material. What is the advantage of high permeability? Yes, if permeability is very high, magnetizing current will be very, very low. Okay, generally for transformer we will use CRGO steel, and CRGO steel will offer very high permeability. That's why magnetizing current was very low. It is approximately 4 to 5% of rated current. So magnetizing current is approximately 4 to 5% of rated current. That means if rated current is 100% magnitude, then magnetizing current is very, very less, which is approximately 4 to 5% only. Okay. So as I mentioned already, magnetizing current is a purely reactive component and lags the supply voltage by 90 degrees. You can see this is the phasor diagram representing that. So here we have the supply voltage, guys, and you see that magnetizing current was here. Just a moment. Yes, magnetizing current was here. So you can understand from the supply voltage, the magnetizing current was lagging by 90 degrees. Okay. Yes. Fine. So let's move to the next concept in a transformer, that is EMF equation of a transformer. So as I mentioned, transformer will have at least two windings, namely primary winding and secondary winding. Sometimes we may use three windings also, known as tertiary winding, that generally we will come across in three-phase transformers. Okay. Now what is the formula for induced EMF across each winding? Very simple. Yes, first one, primary induced EMF. The primary induced EMF of the transformer is 4.44 phi m F into N1, where N1 is number of turns we are using in primary winding, and phi m is maximum flux. Okay, and you can replace this flux. We know flux density is equal to flux per cross sectional area of the core. If you cross multiply, flux is equal to density into cross sectional area. But in the formula we have a maximum flux, therefore I have to use maximum density. That's why this phi m can be replaced by Bm into cross sectional area. Therefore you can use any formula. Okay, so 4.44 Bm cross sectional area frequency into number of turns. So where Bm is maximum flux density of the core and F is supply frequency. This is primary induced EMF equation. Next, secondary induced EMF, that is the mutual induced EMF. 4.44 phi m F into N2. So what is the only difference between primary EMF equation and secondary EMF equation? The number of turns. Primary EMF has N1 number of turns, but secondary induced EMF has N2 number of turns. Frequency will be same, guys. Frequency will be same. That is why transformer is called as constant frequency device. Constant frequency means whatever frequency we gave to the primary winding, same frequency will be induced in the secondary winding as well. Okay, only the number of turns will be different. Now you can see the observations from EMF equation. You see, if I take the ratio from primary EMF E1 by secondary induced EMF E2. Everything is the same except number of turns. Therefore, we will get N1 by N2. This is what we call it as turns ratio of a transformer. Turns ratio of a transformer. Also, you can separate E2 from this formula. If I separate E2, that will be N2 by N1 times of E1. And this ratio, N2 by N1, is what we call it as transformation ratio. Transformation ratio represented with the letter K. K is nothing but a transformation ratio. Therefore, I can write E2 is equal to K times of E1. Okay, K is known as a transformation ratio. So you can understand the difference between turns ratio and transformation ratio. Turns ratio is N1 by N2, primary to secondary. Transformation ratio N2 by N1, that is secondary to primary. Okay. Also, you can cross multiply this relation. You can get one more formula, that is, you take N1 to the left side, E2 to the right side. You can also write E1 by N1 is equal to E2 by N2. So this ratio E1 by N1 is known as voltage per turn on primary side. E2 by N2 is voltage per turn on secondary side. So this is voltage per turn. It is not the voltage, it is voltage per each turn. Therefore, and you can easily understand the voltage per turn on primary side is exactly equal to voltage per turn on the secondary side. Okay. Fine. Now, what are the other observations from the EMF equation of transformer? You see, I will write down the voltage equation. Voltage is equal to 4.44 into Bm cross-sectional area frequency into number of turns. If it is a primary number of turns, this is a primary voltage. If it is secondary number of turns, it is secondary voltage. Okay, that's all right. Now just imagine I have two transformers with me in my laboratory. Both transformers are working at same voltage level. Let us say voltage is same in both transformers. Number of turns are same in both transformers. Frequency is also same in both transformers. Okay, voltage, number of turns, frequency, all are equal. Then tell me what is the relation between density and cross-sectional area. So you can write now cross-sectional area is inversely proportional to maximum flux density. And can I say cross-sectional area of core will definitely decide the size of the transformer for sure. Therefore, cross-sectional area will depend upon the size of the transformer. So, size is inversely proportional to maximum flux density. And our aim is always to design the transformer to have a lower size or higher size, lower size. And in order to reduce the size of the transformer, we have to operate a transformer at higher flux density. Higher flux density. Okay. Therefore, try to operate the transformer at higher flux density, thereby the size of the transformer will reduce. So the moment I said size reduces, indirectly the cost will also reduce. Okay, this is the reason why we will use CRGO steel in transformer, because compared to normal steel, if I use CRGO steel, flux density will increase. Okay, because for a normal steel, maximum flux density was 1.2 to 1 to 1.2 Tesla. Whereas for CRGO steel, the maximum flux density will be 1.5 to 1.7 Tesla. Therefore, by using CRGO steel, flux density can be increased, thereby the size of the transformer can be reduced. Okay, this is one observation. Now, the second observation is, look at the voltage equation once again. Voltage is equal to 4.44 Bm cross-sectional area frequency into number of turns. Imagine I have once again two transformers with me. Yeah, two transformers with me. Both the transformers are operating at same voltage level. Let us say voltage is the same. Both the transformers are having the same number of turns. Both the transformers are operating with the same flux density also. Let us say voltage, density and number of turns are equal in both transformers. Then what is the relation between area and frequency? Therefore, cross-sectional area is inversely proportional to frequency. We know cross-sectional area of core will definitely decide the size of the transformer. So size is inversely proportional to frequency. So from this equation, I can say the transformer which is to be operated at higher frequency will have a lower size. Lower frequency will have higher size. Suppose if I wanted to compare a 50 Hz transformer with a 60 Hz transformer, obviously which transformer will have less size? The transformer which is operating at 60 Hz. Because the frequency is high, the size will be less. But in India, entire power system will be operated at what frequency? 50 Hz only. Okay, but of course, audio frequencies, radio frequencies, or you can say power electronic circuits, the frequency may be different. The frequency will definitely impact the size of the transformer. Okay, yes, this is another important observation. Okay, just a moment, guys. హలో చెప్పండి
సార్ ఉండరాల వరకు లక్ష్మీకాంత్ అండి.
Okay, sorry, I just got a call. So now let us see the next observation, transformer during no load condition. So how does a transformer behave under no load condition? Some important points we will study. So this is a transformer I have selected. The primary winding has N1 turns, secondary winding has N2 turns, and I don't connect any load on the secondary. That is means transformer is under no load condition. But the primary winding I will be connecting across an AC voltage source. The moment when AC voltage source was connected, immediately the transformer will draw a current known as no load current I0. Okay, we call it as the current drawn by transformer at no load. Okay, that is why it is no load current. Now this no load current I0 will have two current components in it. One is magnetizing current I mu. Why I am using a suffix mu? Because I told you already, magnetizing current will depend upon permeability of the magnetic core. As a permeability is deciding the magnitude of magnetizing current, that's why I am using suffix mu. And there is another current component drawn by transformer known as loss component current, indirectly iron loss component current IW. Okay, so this I0 will have two components in it. Okay, one is I mu, another one is IW. This I mu is nothing but the current responsible to create flux in the transformer core. Okay, we know flux will be created whenever current is passing through it, and that flux is what we call it as mutual flux or main flux of the transformer. That flux will link both primary as well as secondary, thereby self EMF will induce across the primary winding and mutual EMF will be induced across the secondary winding. Okay, but at the same time there is another current drawn by transformer known as IW, which is known as iron loss current component. That means the current responsible to create losses within the core medium of the transformer. Okay, so I mu, magnetizing current. In normal classes we use it to explain in a more detailed manner what is I mu, what is IW, why IW is separately used, etc. But this is a quick review session. I would like to give you only the brief points or bullet points which will help you to revise the subject quickly. And then IW, this is iron loss current component. Okay, as the name itself is indicating, this IW will represent the iron losses present in the transformer core. Okay, all right. Now most important thing is how to represent I0. I must say I0 is a sum of these two currents, but you should not add them algebraically. We have to add them vectorially. Okay, why? Because out of this IW and I mu, I told you already I mu is a purely reactive component, lags the voltage by 90 degrees. This is a purely reactive component. Whereas IW is a purely active component. Why it is active component? Because I told you IW will represent iron losses in the transformer. We all know loss is nothing but an active power. Okay, loss is always an active power. So as loss is representing active power, this IW is a purely active component and I mu is a purely reactive component. So when one component is active, another component is reactive, we have to add them vectorially like this. See here. So I naught is equal to IW plus I mu, vectorially we have to add, where IW is iron loss component and its magnitude is around 1 to 2% of rated current, important. Whereas I mu is magnetizing current and its magnitude is 4 to 5% of rated current. Okay, that means who is dominating? Yes, magnetizing current is dominating, 4 to 5%. Loss component current is just 1 to 2% only. Now let us try to draw it on the phasor diagram. First let us mention IW. IW is a purely active component. Active component means, can I say it is a resistive component? Yes or not? We have three elements in power system: resistance, inductance, capacitance. Yes, which element will represent active component? Resistive component. Therefore, the current will be in phase with voltage. You see, this is a supply voltage. Therefore, IW is in phase with the supply voltage. That's why it is active component. Next, what about I mu? I told you I mu is a purely reactive component lagging the voltage by 90 degrees. This is voltage. Lagging means clockwise by 90 degrees. So here comes the magnetizing current. Okay, so draw the phasor diagram in such a way that magnetizing current is more magnitude, IW is less magnitude. This was 4 to 5%, this was 1 to 2%. Then what is the resultant current, which is known as no load current? Yes, vectorially you have to add. So I must say resultant current will come here. This is what we call it as no load current I naught. Okay, this is 4 to 5%, this is 1 to 2%. If you add them vectorially, this will come around 5% of rated current. If rated current is 100%, then no load current will be approximately 5%. And then this angle is what we call it as no load power factor angle, represented with the letter phi naught. Generally, power factor angle means it is the angle between voltage and current. This is the supply voltage, this is the current. So the angle between voltage and current is what we call it as no load power factor angle phi naught. Okay, and you tell me one thing, you try to answer the points in the chat box. So remember one thing, guys, all your questions, if you have anything in the, you please post in the chat box. Okay, I will try to give reply to each and every message after the session. At the end of the session, I will answer all the questions. Okay, because while delivering the lecture, I can't answer your questions. Keep posting whatever the doubts you have in the chat of the lecture, and I will answer after the session. Okay, fine. Now you see that this is a power factor angle, and you try to examine, as I mu was more in magnitude, that means no load current is highly active or highly reactive? Highly reactive. Okay, I naught is highly reactive. As it is highly reactive, no load power factor will be a poor power factor or better power factor? Very poor power factor. So the no load power factor cos phi naught is a poor power factor. So usually it will be in the range of 0.2 to 0.3 lagging. So any power factor which is less than 0.5 is considered as a poor power factor in power system. So if I ask why no load power factor is very poor, then the answer is because no load current is dominated by reactive component rather than active component. Okay, right. Fine. So how to add both of them? This is I mu, this is I naught. Vectorially we have to add. One is a purely reactive, another one is a purely active. So when I add vectorially, yes, this is the formula. I naught is equal to square root of IW square plus I mu square. Important. And you see IW is active component, right? So active component means, can I say I naught times cos phi naught? I mu is reactive component, therefore I naught times sin phi naught. Okay, so IW is I naught cos phi naught, I mu is I naught sin phi naught, where cos phi naught is what we call it as no load power factor of the transformer. Correct? Okay. So this is about transformer under no load condition, and this is the equivalent circuit for the transformer at no load. Yes, you see the no load current drawn by primary, secondary is open circuit. This I naught will have two components in it. Important thing is, one is this I naught has two components. KCL you have to apply. This is a purely active component. That's why IW was represented using a resistive component. And as I told you, IW represents what? Iron loss or core loss. As it is representing core loss, we are calling this resistance as RC, core loss resistance. Okay, RC, core loss resistance. Why resistance is only used? Because IW is a purely active component. And another current is I mu, which is a purely reactive component, and it is lagging the voltage by 90 degrees. That means it is a purely inductive component. If it is leading the voltage by 90, it must be capacitor component. But here I mu was lagging the voltage by 90 degrees. Therefore, it is a purely inductive component. That's why an inductor is used, and we call it as magnetizing reactance. Okay, magnetizing reactance. All right. So let us separately discuss both of them. Yes. So you see, if I apply KVL equation or nodal analysis, can I write RC is equal to V1 by IW? RC is equal to V1 by IW. Important thing is IW is equal to I naught cos phi naught. Oh. Similarly, XM, you can apply voltage here. Voltage is V1, current is I mu. So XM is equal to V1 by I mu, where I mu was I naught sin phi naught. Oh, okay. Remember, XM is a magnetizing reactance, and that too, this is an inductive reactance. As it is the inductive reactance, can I write XM is equal to 2 pi F into L, where L is again self-inductance. Where L is equal to, you remember formula for self-inductance, N square by R. Clear? Okay. Now we will try to answer a simple question related to the no load condition of a transformer. This is the question in GATE 1997. Just read the problem. A voltage V is equal to 400 sin 314.16 T is applied to single phase transformer on no load. If the no load current of the transformer is 2 sin 314.16 T minus 85 degrees, then magnetizing branch impedance will be approximately how much is the question. You see, the supply voltage was given. First thing, what is the voltage given? 400 sin 314.16 T. This is like 400 sin omega T. And transformer is at no load. That means what is the no load current? I naught is equal to 2 sin 314.16 T minus 85 degrees. Okay. That means you can clearly understand the supply voltage was at 0 degrees and the no load current was at minus 85 degrees. That means, can I say no load current was lagging the voltage by how many degrees? 85 degrees. Okay. Therefore, I naught is lagging the supply voltage by 85 degrees. Now what they are asking you, they are asking what is the magnetizing branch impedance will be. Magnetizing branch impedance they are asking. Okay, magnetizing branch impedance will be. So magnetizing branch means indirectly this shunt branch only. What is the overall shunt branch impedance they are asking? Can I say this overall impedance means, is it simply voltage by current only? Okay, voltage by current. Voltage is V1, current is I naught, but this voltage and current must be RMS values I have to use. Okay, here is it looking like 400 maximum voltage? So therefore, what is RMS value of the supply voltage? It is 400 by root 2. Correct? What is RMS value of the no load current? RMS value is equal to 2 by root 2. But anyway, if I wanted to find out impedance Z0 magnitude, it is simply supply voltage by no load current. Anyway, root 2 will cancel. So that was 400 by root 2 divided by 2 by root 2. Is it not 200 ohm? Okay. But impedance will have angle, right? So therefore, Z0 is equal to 200 at an angle. Yes, you can see here the current was lagging the voltage by 85 degrees. Therefore, the impedance angle was 200 by 200 at an angle 85 degrees ohm. That is option B. Sorry, not option B. Option B has minus 85 degrees, but impedance will have a plus sign. Okay. Option C. 1 second. 200 at an angle 85 degrees. Okay. So Z0 is simply V by I0. V was 200 by root 2 at an angle 0 degrees because voltage is at an angle 0. Current is 2 by root 2 at an angle minus 85 degrees. Current was lagging the voltage by 85. So root 2 will cancel. 200 by 2. I think this is not 200. This is 400, guys. Voltage was 400. Yeah. This was 400 by root 2. 2 by root 2. So the answer is 200 at an angle minus 85 goes to the numerator plus 85. Okay. Fine. That is about no load condition. Now let us try to understand how a transformer will behave under loaded condition. Okay. So currently this transformer is under no load condition. You can understand from the primary only low load current I0 was drawn. Secondary is open circuited. Now what will happen? The moment you connect a load on the secondary side, a current will be generated by the secondary known as I2. Okay, so this I2 will create a flux, whenever this current I2 passing through secondary winding will create some flux, and according to Lenz's law, that secondary flux of phi2 will oppose the main flux. Phi2 is opposing the main flux. And in order to cancel this phi2 or in order to neutralize this phi2, one more current will be drawn by primary winding. Okay, let me use a different color. One more current will be drawn by primary winding. We call that current as I1 dash. So this I1 dash will create one more flux known as phi 1 dash. And finally at a steady state, this phi 1 dash and phi 2 will neutralize each other. Once phi 1 dash and phi 2 neutralize each other, then what is the only flux that will be available in the transformer? Main flux only, indirectly mutual flux only. That is why transformer is also known as a constant flux device, because whether it is no load condition or loaded condition, the flux remains constant. Okay. So what happens under loaded condition? These two fluxes will cancel. Now finally you tell me how many currents are available in the primary. Two currents are available, I0 and I1 dash. Therefore the total primary current, I1, this is equal to I0 plus I1 dash. Okay, remember I0 is the no load current, and when the load was connected on the secondary, automatically a current is drawn by the primary known as I1 dash. So the total primary current is I0 plus I1 dash. Here you need to understand this I0 is approximately 5% of the rated current. We discussed already no load current, but this I1 dash is 95 to 96% of rated current, and if you add both of them, this is the total rated current 100%. Therefore, if you look at this entire equation, which current is very, very small? Yes, no load current I naught is very, very small and you can almost neglect it. Suppose if no load current I naught is neglected, then what is the total primary current will be? I1 is equal to I1 dash only. Okay. So I can write, if I naught is neglected, okay, then I1 is equal to I1 dash. And most importantly, this I1 dash and this I2 will have a relation. Okay, what is the relation? I1 dash is equal to K times of I2. I am not doing the derivation, but you have to remember this equation. I1 dash, that is the primary side loaded current, is equal to K times of I2, where K is known as transformation ratio. We know transformation ratio is N1 by N2 or N2 by N1, N2 by N1. And if I substitute that here, so I1 dash is how much? K times of I2. So from that, I1 is equal to, what is K? N2 by N1 times of I2. And if you cross multiply N1 this side, or you take I2 to this side, I1 by I2 is equal to N2 by N1. Important. So according to this equation, you can see current ratio I1 by I2 is equal to N2 by N1. That means 1 by 2 is equal to 2 by 1. That indicates it is inverse proportionality or direct proportionality, inverse proportionality. Whereas voltage ratio, if you see, we discussed earlier voltage equations, V1 by V2 or E1 by E2, that is equal to N1 by N2. So voltage ratio was directly proportional to turns ratio, but current ratio was inversely proportional to turns ratio. And if you combine both of them, you can understand one more equation, that is V1 I1 is equal to V2 I2. So this is what we call it as input volt ampere power is equal to output volt ampere power, or primary volt ampere power is equal to secondary volt ampere power. Yes, because voltage into current is nothing but volt ampere power. So volt ampere power on primary side is equal to volt ampere power on secondary side. So transformer is a constant volt ampere device. Whatever the volt ampere power you give on the primary, the same volt ampere power will be delivered to the secondary. Okay. But remember, all this information is only when I naught is neglected. If I naught is not neglected, all these formulas will not be valid. Okay, but it is a valid assumption. Why? Because no load current I naught is very, very small. So neglecting I naught is definitely not going to be a big error. Okay, so it is a valid assumption. Fine. Now we will try to understand the phasor diagram of the transformer under loaded condition. Currently, I have shown you the flux and voltage phasors. First, let me draw no load current I naught. So generally we know no load current I naught is lagging the voltage by a power factor angle known as phi naught. Okay, this is no load condition. Now the load is connected on which side? Yes, remember, load was connected on secondary side. When load was connected on secondary side, I2 current will first flow or I1 dash current will first flow. Of course, polarity I have to mark. Okay, I2 current will first flow or I1 dash will first flow? Yes, I2 will first flow. Suppose if the load is a lagging power factor load, because we know majority of power system will have RL type load. So let us consider a lagging power factor load. So if load is lagging power factor, then this I2 will lag the voltage, right? This is the voltage E2, secondary voltage E2. So I2 is lagging the secondary voltage V2 or E2 by a secondary power factor angle phi 2. Now this I2 will create a flux known as phi 2, this flux phi 2, and to neutralize this flux phi 2, one more current was drawn I1 dash, so that I1 dash will create additional flux phi 1 dash. Both will neutralize each other, that means both are opposite to each other. Therefore, I1 dash will be exactly opposite to I2. This is I1 dash. Remember, I1 dash is exactly opposite. And what about magnitude? K times of I2. Now tell me what is the total primary current. Total primary current means it is I naught plus I1 dash, sum of both. So you see I naught and I1 dash, if I add both of them vectorially, I will get total primary current I1 somewhere here. Okay. So this is the total primary current I1. Then what about primary power factor angle? Yes, this is the primary power factor angle phi 1. Okay. So this is the phasor diagram of the transformer under loaded condition. Okay, just observe this diagram. I'll be back in a minute. Thanks. Okay, so this is about the phasor diagram of the transformer under loaded condition. See some observations from this phasor diagram. You can see, okay, suppose if no load current I0 is neglected, then what is the primary current I1? Is it equal to I1 dash? So if I1 is equal to I1 dash, then secondary power factor angle phi 2 and primary power factor angle phi 1 becomes equal. But if I0 is not neglected, if I0 is considered, then secondary power factor angle phi 2 and primary power factor angle phi 1 will not be equal. Okay, this is a minor point all of you have to remember. Suppose if I say secondary power factor is 0.8 lagging, primary power factor may not be 0.8 lagging. Why? Because both angles are not equal. This is when I0 is considered. But if I0 is neglected, that is indirectly ideal transformer. In ideal transformer, no load current is neglected, then secondary power factor and primary power factor will be same. Understand? Okay. All right. Now we will try to answer a question related to this phasor diagram concept. So see that loaded condition concept. This is a question in GATE 2014 exam. Let's see the problem. The load shown in the figure absorbs 4 kilowatt at a power factor of 0.89 lagging. You can see the load is on secondary side. The voltage was 110. And assuming the transformer to be ideal, what is the value of the reactance X to improve the input power factor to unity? To improve the input power factor to unity. So one thing is missing here. This is 220 volt. Okay, that is 220. So what is this reactance X value so that we can improve the power factor to unity on the input side? So what I will do is that simple thing. First let me calculate what is the load current I2. So if I calculate load current I2, can I say I2 is equal to voltage V2 by the load impedance? What is the voltage V2? 110 divided by the load impedance. I don't know the load impedance, but power was there, right? Instead of impedance, we better use power equation. Okay, so let me change this formula. The load power was given. How much is the load power? 4 kilowatt. Yet how much power factor? 0.89 lagging. So I can write 4 kilowatt means active power. Okay, P2 is equal to V2 I2 cos phi 2. Power was 4 kilowatt, that is 4000. V2 was 110. I2 we don't know, but power factor was known 0.89. Therefore, we can find out the magnitude of current I2. Okay, so let me bring my calculator. You can also post me the answers in the chat box. Okay. Okay, so 4000 divided by 110 into 0.89. So it was 40.85 ampere, but I need to use the angle because the power factor was 0.89 lagging. So that means the angle will be cos inverse 0.89. That was 27.12 degrees. 27.12 degrees, that to negative angle. Why? Because it is a lagging power factor. This is a secondary current I2, guys. Now what you do is that transfer this secondary current I2 to primary side, we will get I1 dash here. What is the magnitude of I1 dash? Okay, let me go to the next page. So we know I1 dash is equal to K times of I2, where K is N2 by N1. N2 by N1 means you can write V2 by V1 times of I2. What is V2 by V1? That is 110 by 220 into I2. What is I2? That was 40.85 at an angle 27.12 degrees. 40.85 at an angle minus 27.12 degrees. This will give you I1 dash. Okay, so it will be indirectly 40.85 by 2. So is it not 20.425 at an angle minus 27.12 degrees? This is I1 dash. Okay. So I got I1 dash magnitude. Remember this is I1 dash. Okay, now the question is, what is the reactance X value so that overall power factor becomes unity? Okay, to understand the overall power factor to be unity, a very simple thing is, this current, total current, let us say total current I, this should be at an angle 0. Okay, so because supply voltage will be at an angle 0, if a supply current is also at an angle 0, then only I can say overall power factor is unity. I can say this current becomes at an angle 0. Let us say this is Ix. So can I apply KCL equation there? So I is equal to Ix plus I1 dash. Okay. So therefore, I can write I is equal to Ix plus I1 dash. Okay. So this is Ix plus, what is I1 dash? I1 dash means 20.425 at an angle minus 27.12. Let me resolve this into real part and imaginary part. What is the real part of it? 27.12 cos. So the real part is 18.17 minus j. What is the imaginary part? 27.12. Sine term will be imaginary part, right? Into 20.425. So 9.31. This is the imaginary part. Okay. So real part 18.17 minus j 9.31. Now the point is, this current, total input current I, this should be at an angle 0. Can I say this will be at an angle 0 only if it has real part? And if imaginary part is 0, then the overall current will have only real part. Only real part means current is at an angle 0. That means what? This Ix should cancel this reactive component. Okay, so if this Ix cancels this reactive component, then the overall current will have only real part. Only real part means that current is set to be at an angle 0. Therefore, I can write Ix is simply equal to cancel this, it must be plus j 9.31. This should be the value of Ix. If this is the value of Ix, then what is I? Therefore, I is equal to 18.17 at an angle 0. Correct or not? But the question is, they are asking what is the current drawn by reactance X or what is the impedance of reactance X? What is the impedance of reactance X? So to find out the impedance of reactance X, I just need voltage across this reactance. Let us say that is Vx, and current passing through the reactance Ix. So if I take Vx by Ix, that will give you the reactance X. So already this voltage is how much? This is 220. You know current passing through this particular branch. What is that current? 18.17. Then if you apply KVL equation, can I apply KVL equation here? Yes, what is the KVL equation? So it will be, I will redraw the circuit. This is 220 at an angle 0. I have a resistance of 1 ohm. I have a reactance X here. Also, I have a transformer here. Okay, this is I1 dash. This is Ix. This is I. And voltage across this reactance, let us say this is Vx. Okay, so what I am asking you is apply the KVL equation here. Already this current is at an angle 0. So what is the KVL equation? 220 at an angle 0 is equal to, what is this current I? I we found 18.17. 18.17 at an angle 0 into the resistance 1 ohm plus Vx. Correct? Is it or not? Plus Vx. So from this, Vx is equal to 220 minus 18.17, because both angles are 0 only. Algebraically I can proceed. So, yes, Vx is equal to 220 minus 18.17. I think it was 201.83 volt. So the moment you know Vx, then what is impedance of X? That is Vx divided by Ix. So what is Vx? 201.83 divided by, what is Ix we got? Ix is J9.31. I think I need only the value of reactance. I need only magnitude of the reactance. Anyway, I will substitute J9.31. J9.31. So if you complete it, so minus J 21.67 ohm, and that negative reactance represents that X is a capacitor. You just need a capacitor as a reactance here. Okay, and what is the value of that capacitor reactance? It was 21.67, so that overall power factor can be improved to unity. So what I did in this question, I must say this is like an electrical circuit question rather than transformers question. Based on the given output power, I calculated secondary current. Then I transferred this secondary current to primary side using the turns ratio. I got I1 dash. And then I1 dash plus Ix summation should give you the total input current I. And as I said, overall power factor has to be improved to unity. This I must be at an angle 0. So I applied the KCL equation. Overall current will be at an angle 0 only if reactive part cancelled. Can I say reactive part will cancel if Ix is exactly opposite to this value, plus J9.31. That is how I found overall input current I, and then I will apply KVL equation. I got Vx. If I know Vx, I can find out what is the reactance X. Okay, that's it. Clear? So that is about transformer under loaded condition, an example question, an important model as well. Now we will move to our next important topic in a transformer, that is equivalent circuit of a transformer. Remember, to draw equivalent circuit of a transformer, we have to consider four important effects. One is permeability of the core. Yes, we are using finite permeability of the core. Next, we have to represent core losses in the transformer in the equivalent circuit. We have to represent copper losses in the transformer in the equivalent circuit. And also we have to show the leakage flux of the transformer in the equivalent circuit. Okay. So this is the complete equivalent circuit of a transformer. So here this R1 and R2 represents copper loss in a transformer. X1 and X2 represents leakage reactance of the transformer. So X1 is primary leakage reactance, X2 is secondary leakage reactance. This RC will represent core loss value, okay, as we discussed already, finite core loss and iron loss. And this XM will represent permeability. We know the current drawn by this XM is nothing but a magnetizing current, and I told you already magnetizing current is inversely proportional to permeability. Therefore, the permeability of the core will affect magnetizing current. Magnetizing current is a reactive component shown by this reactance. So this is the complete equivalent circuit of the transformer, and the turns ratio is N1:N2. But the disadvantage of this equivalent circuit is it is two isolated electrical circuits. And in order to make transformer as a single electrical circuit, what we will do? We will transfer the parameters. You can transfer either primary to secondary parameters, or you can transfer secondary parameters to primary also. First of all, what is the purpose of transferring the parameters? Is simple, to represent the entire transformer like a single equivalent circuit. Now what I am going to do is that I wanted to transfer secondary parameters to primary side. Let's see. Yes, this is happening. If a secondary resistance was transferred to primary side, its resistance value will change to R2 dash. If a secondary reactance transferred to primary side, its reactance will change to X2 dash, like this. Yes, R2 dash, X2 dash. Now what is R2 dash? It is a secondary winding resistance when referred to primary side. X2 dash, secondary winding leakage reactance when referred to primary side. V2 dash, load voltage referred to primary side. Understand? So these are the detailed parameters when they are transferred to primary side. Now it is a single electrical circuit or two isolated electrical circuits, single electrical circuit. But you may have a doubt here, what are the formulas? How to transfer parameters? There will be derivations for that, but we are not doing derivations right now. But my intention was, I wanted to give a simple shortcut so that you can remember all these parameters easily. Let's see. Remember, the simple rule is, to which side you are transferring the parameters. Okay, see, I am transferring this resistance to the primary side. As it is transferring to primary side, the value of R2 dash is equal to, I am going to primary, so primary by secondary number of whole square into its original value R2. Suppose if you transfer primary resistance to secondary side, then it will become R1 dash. If R1 goes to the secondary, then R1 dash value will become, as I am moving to secondary, secondary should come in the numerator. Secondary by primary whole square times of its original value R1. Okay, a simple rule. So in the same manner, can you tell me what is R2 dash now? R2 dash, it was transferred from secondary to primary. As we go to primary side, it is primary by secondary whole square into R2. What is the X2 dash? We went to primary, so it is primary by primary N1 by N2 whole square times of X2. Okay. Also, when you transfer parameters to secondary side, now I2 dash and I1 dash both are equal. We know I1 dash is equal to K times of I2. Therefore, I2 dash, I1 dash both are equal. That is K times of I2, where K is N2 by N1. Clear? Okay. So this is the equivalent circuit of transformer referred to which side? Primary side. All parameters are referred to primary side. This is a circuit diagram referring the transformer to primary side. Now, I wanted to further simplify this equivalent circuit, because if you look at the circuit, I have two loops. Loop number 1 here, loop number 2 here. Therefore, writing KVL equations becomes difficult when you have two loops. I wanted to make it more simple. In order to make it more simple, what we will do is that, simple. Let us shift this shunt branch to the source side, like this. Actually, the shunt branch should be at the middle of the circuit. But in order to make the circuit simple, I am shifting this shunt branch to source side. Why I am flexible to shift this shunt branch? Why? Because the current drawn by this shunt branch is nothing but no load current, And we know no load current is very small or very large, very small. That's why you can shift it to any side you want. The errors becomes very low, okay, because no load current is very, very small. So what is the advantage of shifting shunt branch from the middle of the circuit to source side? Very simple. These two branches are now in series. As these two branches are now in series, can I combine R1 and R2 dash together as a single resistance? Yes. That is capital R01. Because everything referred to which side? Primary side. That's why suffix 1 you need to use. And I'm using a capital R. Remember guys, if I use a small r, they are individual winding resistances. When I use a capital R, that means it is the total effective resistance, okay, referred to primary side. Similarly, X1 and X2 dash I can combine like a single reactance, that is X01. Okay. So circuit becomes more simple. Clear? Now we will try to answer one question related to this transferring of parameters from one side to another side. You see this question. A single phase transformer has a turns ratio 1:2, turns ratio 1:2, and it is connected to a purely resistive load. It is connected to a purely resistive load as shown in the figure. The magnetizing current drawn by the transformer is 1 ampere. See, magnetizing current was 1 ampere. Secondary current is 1 ampere. Secondary current is also 1 ampere. If core losses and leakage reactances are neglected, see, core loss neglected guys. Core loss neglected means IW is equal to 0. What is the total primary current is the question. So first let us note down the data. Turns ratio N1:N2 is equal to 1:2. Purely resistive load. Magnetizing current was given. What is the magnetizing current? 1 ampere. But remember, magnetizing current is a purely reactive component lagging the supply voltage by 90 degrees. That's why it has to be written as 1 at an angle minus 90 degrees. Secondary current is also 1 ampere. Secondary current means indirectly I2. That is 1 at an angle 0. Can you guess why I am writing secondary current at an angle 0? Yes, because the load is resistive. We know when the load is resistive, current will be in phase with voltage. So the current is at an angle 0. Next, core losses are neglected. That means IW is equal to 0. What is the total primary current is the question. So tell me, in a transformer, what is the total primary current I1 is equal to? Can I say I1 is equal to I0 plus I1 dash? So first let me calculate I1 dash. What is the formula for I1 dash? I1 dash is equal to K times of I2, where K is equal to N2 by N1 into I2. So according to the given question, N2 by N1 means 2 by 1 into I2 was 1 at an angle 0. Therefore, I1 dash is 2 at an angle 0. So substitute. Therefore, I1 is equal to, again I0 means what? Can I say I0 is equal to IW plus I mu plus I1 dash. Remember, everything we have to add vectorially. But right now IW is 0 because core losses are neglected. Magnetizing current is 1 at an angle minus 90 because magnetizing current is a purely reactive component, and I1 dash is 2 at an angle 0. So I hope you can do this solution now. 2 at an angle 0 plus 1 at an angle minus 90, can I write it as cos 90 minus j sin 90? Okay, so cos 90 is 0, sin 90 is 1. Therefore, the final answer is 2 minus j1. But look at the options. Options are having only magnitude. So when you need only magnitude, it is a square root of 2 square plus 1 square. Angle will be minus tan inverse imaginary part by real part. So when you need only magnitude, then the answer will be root 5. Root 4 is 2, root 5 is more than 2. So 2.24 is the correct answer. But the common mistakes what students will do is they will add this 1 and 2 algebraically and they will say, sir, 3 ampere is the total primary current. That option will also be available, 3. But that is wrong answer. So you should never add anything algebraically, because angles are very, very important, because few currents are active components will be there, reactive components will be there. We have to add them vectorially. All right. Okay, let us move to another question. This is also related to the equivalent circuit of a transformer. Read the problem. The self-inductance of the primary winding of a single phase 50 Hz transformer is 800 millihenry, and that of the secondary winding is 600 millihenry. The mutual inductance between these two windings is 480 millihenry. See, primary winding self-inductance was 800 millihenry. Secondary winding self-inductance is 600 millihenry, and the mutual inductance between both of them is 480 millihenry. Okay, next information. The secondary winding of this transformer is short circuited. See, secondary winding is short circuited. Okay, this is the primary winding of the transformer, and this is the secondary winding of the transformer. Secondary winding is short circuited. Okay, and primary winding is connected to a 50 Hz single phase sinusoidal voltage source. So primary winding was connected to a sinusoidal voltage source. Let's say the voltage is V1. Okay, now the current flowing in both the windings is less than their respective rated currents. So definitely some current will go through primary and some current will go to secondary. Both are less than rated currents only. In this condition, what is the effective inductance seen by the source? From the source, what is the effective inductance we have to calculate? So remember, primary winding has some self-inductance, secondary winding has some self-inductance, and between the two there was some mutual inductance. I hope you studied coupled circuits in electrical circuits subject, and you have to answer this question using coupled circuits knowledge. A very simple point you need to understand here is transformer is a negative magnetic coupling circuit. What is mean by negative magnetic coupling? Very simple. On the primary side, current will enter the dot polarity, whereas on the secondary side, current will leave the dot polarity. Okay, so if I write KVL equation on primary side, what will happen? Primary, the supply voltage was V1. So V1 is equal to, it has a self-inductance already. Let us say self-inductance is L1. L1 into dI1 by dt minus M into dI2 by dt. This is self EMF, this is mutual EMF. But for mutual, why I am writing minus M? Because secondary current was leaving the dot, primary current was entering the dot. So if entering the dot creates a positive EMF, leaving the dot will create a negative EMF. So this is primary KVL equation. So what is L1 given? L1 was 800 millihenry, that is 0.8 Henry dI1 by dt. M was 480 millihenry, that means 0.48 dI2 by dt. We know mutual EMF means it is the EMF induced in primary winding due to secondary current. What is mutual EMF in secondary? Mutual EMF in secondary is the EMF induced in secondary winding due to primary current. Okay, so let us consider this as equation number 1. Okay, next let us go to KVL equation on secondary. But remember, secondary was a short circuit. Therefore, what is the voltage across a short circuit? 0, right? 0 is equal to, let us write self EMF first. Self EMF on secondary 600. That is L2 into dI2 by dt minus M into dI1 by dt. Why minus M again? Secondary current was leaving the dot, primary current was entering the dot. It's a coupled circuits knowledge. Okay, so 0 is equal to, what is L2? 600 millihenry, 0.6 dI2 by dt minus M 0.48 dI1 by dt. You can take this product to the left side. So 0.48 di1 by dt is equal to 0.6 di2 by dt. Separate di2 by dt now. Therefore, di2 by dt is equal to, send 0.6 to the left side, 0.48 divided by 0.6 into di1 by dt. Assume this is equation number 2. Now what you do is that substitute this equation 2 di2 by dt in equation 1. Okay, then what happens? So I will rewrite equation 1. Let me go to the next page. Yes, v1 is equal to 0.8 di1 by dt minus 0.48 di2 by dt. Now what is the di2 by dt? Can I use this value? Yes. So 0.8 di1 by dt minus 0.48 into what is di2 by dt? 0.48 by 0.6. di1 by dt. So I think di1 by dt you can take common. Then the remaining 0.8 minus 0.48 square by 0.6 into di1 by dt. Okay, let me calculate what is this total value. Okay, 0.48 square divided by 0.6. So I'm getting 0.416. 0.416 di1 by dt. This is v1. Okay, then is it looking like the effective inductance? Suppose if you wanted to represent the entire transformer with one single inductance, with a supply voltage v1, supply current i1, then can I write this as v1 is equal to simply, okay, so v1 is equal to L into di1 by dt, simply one single winding. Then that L is nothing but effective inductance, and in place of that effective inductance you have 0.416 henries. Therefore, finally the effective inductance seen from the primary side is 0.416 henries, indirectly 416 millihenries. That is the answer. So the points are very simple. We are asked to find out what is the effective inductance in millihenries seen from the primary side. The answer was 416. Okay, I just wrote the KVL equation, coupled circuit equation, and I just solved both equations and I found the entire formula in terms of a single inductance, that is the effective inductance of the coil. Okay, that's all. All right, so just a moment, we will start power losses in transformer. Okay. All right, so let's see the next concept, power losses in transformer. So there are basically two types of major losses we can observe in transformer. One is iron loss, another one is copper loss. So here iron loss is a constant loss from no load to full load, whereas copper loss is a variable loss. Okay, again iron losses are classified into two types. Okay, one is hysteresis loss. Hysteresis loss means it is the power loss produced within the core medium of the transformer due to alternating magnetization. Okay, because we are exciting transformer with AC supply, so the magnetic dipoles inside the core medium has to change their orientation from one side to another side for every half cycle. So because of that some power loss takes place. We call it as hysteresis loss. And eddy current loss is nothing but it is a power loss which is produced within the transformer core due to circulating eddy currents. You can see this diagram here. If you cut the core at one point, within the cross section some circulating currents are going to be created. Those circulating currents are known as eddy currents, and the loss due to eddy currents we call it as eddy current loss. And we know in order to minimize eddy current losses we will generally do laminations. Okay, a laminated steel core is used rather than a solid steel core. Okay, Now, important thing is what are the formulas to calculate hysteresis loss and eddy current loss. Yes, I have clearly mentioned here. So, hysteresis loss is equal to eta into Bm power 1.6 into F into volume of the core. Here, volume means it is the core volume. Understand? F is the frequency, Bm is maximum flux density, and eta is known as hysteresis coefficient. Okay, and this 1.6 is actually Steinmetz constant. And you know, once transformer construction is completed, the volume of the core and eta will be constant values. Therefore, hysteresis loss is proportional to, directly proportional to Bm power 1.6 into F, where F is the supply frequency. Similarly, we have a formula for eddy current loss also. K into Bm square into F square into T square into volume. Again, this volume is nothing but core volume. This T is the lamination thickness. Okay. Lamination thickness. Alright. So you can write eddy current loss is directly proportional to square of the lamination thickness. And K is conductivity constant of the core. And you know, once construction is completed, this conductivity constant K, lamination thickness, volume, these are all constants. Therefore, eddy current loss is proportional to Bm square into F square. Okay, so simply, what is the formula for Bm again? Bm is again proportional to V by F. This is from EMF equation of transformer. You know, voltage is equal to 4.44 Bm cross-sectional area frequency into number of turns. And you know, once the construction completed, area and number of turns are constants. Therefore, Bm is directly proportional to V by F ratio. Okay. So finally, you can understand from these two formulas that hysteresis loss, okay, is proportional to Bm power 1.6 into F. Eddy current loss is proportional to Bm square into F square. And Bm is proportional to V by F. Therefore, I can easily understood that the value of hysteresis loss and eddy current loss will depend upon voltage and frequency only. Suppose if a transformer is excited from constant voltage and frequency source, hysteresis loss and eddy current loss remains constant from no load to full load. Okay. Right. Now we have to find out the formulas for hysteresis and eddy current losses in two cases. One is if V by F ratio is constant, and the other one is if V by F ratio is variable. Okay. Yes. Very important formulas. If V by F ratio is constant, the formula for hysteresis loss is equal to A into F, where A is proportionality constant. And eddy current loss will be equal to B into F square, where B is proportionality constant. Okay. Therefore, what is the total iron loss? Can I say iron loss is nothing but sum of hysteresis loss and eddy current loss? Therefore, the iron loss will be A into F plus B into F square. Similarly, what is going to be the formulas if V by F ratio is variable? If V by F ratio is variable, hysteresis loss will be equal to C into V power 1.6 into F power minus 0.6. Once again, C is some arbitrary constant, the proportionality constant. V is voltage, F is frequency. And eddy current loss will be equal to D into V square. Therefore, what is the total iron loss? Therefore, the total iron loss is sum of hysteresis and eddy current loss. Therefore, C into V power 1.6 into F power minus 0.6. Eddy current loss D into V square. So this is the formula for iron loss in the two cases when V by F ratio is constant and when V by F ratio is variable. And here A, B, C and D are constants, proportionality constants. Alright, okay, yes. So questions will come directly from these equations. If you remember equations, you can easily answer the questions, okay. So this is about iron loss in transformer. Alright, now the next one is copper loss. We all know that copper loss is mainly due to the resistance offered by transformer winding, okay. So whenever current is passing through winding resistance, definitely copper loss will be produced. And in order to minimize the copper losses, we will generally use low resistance windings. And we know transformer will have two resistances, primary winding and secondary winding. So you can express a copper loss in different ways. Suppose if a primary resistance is on primary side, secondary resistance is on secondary side, then formula for copper loss is I1 square R1 plus I2 square R2, where R1 is primary resistance, R2 is secondary resistance. Suppose if the entire resistance is referred to primary only, suppose the entire resistance is on primary side, then the formula will be I1 square R01. If the total resistance is on secondary, then the formula will be I2 square R02. So what is R01 here? Yes, total resistance referred to primary. Okay, referred to primary. What is R02? R02 is total resistance referred to secondary. Referred to secondary. You can use any resistance to find out copper loss. And important observation is, if you look at copper loss carefully, copper loss is proportional to current or proportional to square of the current? Yes, copper loss is directly proportional to square of the load current. That means whenever load changes, current will change. If current changes, copper loss will also change. That is why copper loss is a variable loss. Also, you see how to find out copper loss at X percentage load. Yes, as loss is proportional to square of the current, at X percentage load, the current will become X times of rated current. Suppose if full load current is I, let us say, then what is half load current will become? Half load current will become 0.5 into I, because half of the rated current. What is current at 30% load current? If it is a 30% load, the current will become 0.3 into I. Therefore, similarly at X percentage load, it is X into I. So in place of current, you just replace X times of rated current. Therefore, copper loss at X percentage load is X square times of rated copper loss. Rated copper loss or full load copper loss, both are same. This is an extremely important formula. Okay, so whenever you are representing copper loss in a transformer, you should not say simply copper loss. You have to be very specific. That is the copper loss at how much? Just a moment. Sorry. Yes. So this is the copper loss at X percentage load. Okay. Where X is the per unit load. Suppose if I am talking about a full load, X will be equal to 1. Half load, X becomes 0.5. 70% load, X equal to 0.7. Like that, whenever load changes, X will change. Fine. One more important formula that we have to remember is per unit full load copper loss. A very important formula. Per unit full load copper loss. Yes, per unit full load copper loss means it is the actual full load copper loss by VA rating of the transformer that will be equal to R per unit. Very important. Okay. So if you have R per unit value with you, R per unit is equal to full load copper loss divided by VA rating of the transformer. This will help us more in efficiency calculations, voltage regulation calculations, etc. So if you know full load copper loss and VA rating of the transformer, we can find out per unit resistance of the transformer, and this is also equal to per unit full load copper loss. Okay, right. Now let us try to answer a question related to losses in transformer. This is a question in GATE 2021 paper. Just read the problem. In a single phase transformer, the total iron loss is 2500 watt at a nominal voltage of 440 volt and frequency 50 hertz. The total iron loss is 850 watt at 220 volt and 25 hertz. Then at a nominal voltage and frequency, what is the hysteresis loss and eddy current loss is the question. First of all, there are two cases in the problem. In the first case, voltage was 440 and the frequency was 50 hertz. This is like case number 1. In the second case, voltage was changed to 220 and frequency was changed to 25 hertz. So two cases I have to note down. In case number 1, yes, voltage was equal to 440 volt, frequency was equal to 50 hertz. And what is the total iron loss in this situation? 2500 watt. Okay, the total iron loss in the first case is 2500 watt. Okay, next time in case number 2, voltage and frequency were modified. What is the voltage now? 220 volt and the frequency was 25 hertz. So the total iron loss in the second case was equal to 850 watt. Now using these two cases, we have to find out what is hysteresis loss and eddy current loss in a nominal case, that is case number 1. Okay, so first let us check whether V by F ratio is constant or variable. Yes, you can understand V1 by F1, 440 by 50, V2 by F2, this is 220 by 25. So what is the opinion? V by F ratio constant or variable? Yes, therefore V by F ratio is a constant value. Yes, if V by F ratio is constant, what is the formula for hysteresis and eddy current loss? Therefore, hysteresis loss is equal to A into F. Eddy current loss will be equal to B into F square. Therefore, the total iron loss is equal to A into F plus B into F square. Now, what is the iron loss in the first case? 2500. 2500 is equal to A into first case frequency 50, B into 50 square. In the second case, what is iron loss? 850. Okay, 850 is equal to A into AB are constants, they don't change. But what is the frequency in the second case? 25 hertz plus B into 25 square. Now if I solve these two equations, I will get the values of constants A and constant B. So the moment I know constant values A and B, I can separately calculate hysteresis loss and eddy current loss. Okay, so let us solve these two equations. Let me get my calculator. You can try, okay? You can try and let me know in the chart. So what I'll do is that first equation I will divide with 50 on both sides. Therefore, this equation will change. What if I divide 2500 with 50? It will become 50. 50 is equal to A plus B into 50. Divide second equation both sides with 25. Then 850 by 25, this is 34. 34 is equal to A plus B into 25. Now I think these two equations are easy to solve. What if I subtract? Left side will become 16 is equal to A will cancel, right side will become 25B. So first you will get B value. So B is equal to 16 by 25. So 0.64. The moment you know B, I think A value you can easily calculate. So it will become 0.64 into 25. Yes, A is equal to 18. Okay, if I made any mathematical mistakes, please try to correct them. Okay, because I am also using calculator just like you. So now I have A value and B value. So can I calculate hysteresis loss and eddy current loss at a nominal voltage and frequency? Yes, I can do that. Okay, so what is the formula for hysteresis loss? A into F. What is the value of A? 18. At what frequency we are asked to find out hysteresis loss? Nominal frequency, that is 50 hertz. Therefore, hysteresis loss is 18 into 50, that is 900 watt. Similarly, find out eddy current loss, B into F square. What is the value of B we got? B was 0.64. So 0.64 into 50 square. Okay, so 50 square into 0.64, it is 1600 watt. Therefore, hysteresis loss was 900, eddy current loss was 1600. So you can see second option will be correct, because the answer we need hysteresis loss and eddy current loss. Okay, so second option, hysteresis loss 900, eddy current loss 1600. At which condition? This is at a nominal voltage and frequency. So when the question was given related to iron losses, the first duty is we need to check whether V by F ratio is constant or variable. Okay, all right. Now let's move to our next discussion, open circuit test and short circuit test. Yes, very important. There are many questions based on these testings in previous GATE exams. So what is the purpose of open circuit test? Open circuit test is used to determine rated iron loss of the transformer. Okay, iron loss means constant loss. Also, we can find out shunt branch parameters using this particular test. We cannot find series branch parameters. Okay, and also we can separate no load losses. That means we can separate hysteresis loss and eddy current loss. Okay, both of them. Next, during this test, low voltage winding is excited from rated voltage and frequency source. Okay, remember the purpose of the test is to determine iron losses. Iron losses are two types, hysteresis loss and eddy current loss. What is the formula for hysteresis loss? Bm power 1.6 into F. Eddy current loss is proportional to Bm square into F square, and Bm is proportional to V by F. If you look at all these formulas, you can understand both hysteresis loss and eddy current loss are dependent upon voltage and frequency. So when our aim is to measure iron losses, we have to make sure that voltage and frequency are rated values. Thereby, hysteresis and eddy current losses are rated values, and we can find out rated iron losses using this test. That is why during this test, voltage is rated value and frequency is also rated value. And most importantly, OC test will be always conducted from which side? Yes, by default, OC test is always conducted from low voltage side. Low voltage winding is excited. That means which winding is open circuited? High voltage winding will be open circuited. So very important. By default, open circuit test is always conducted from LV side only. Okay, right. So this is the equivalent circuit, or you can say the arrangement. Okay, open circuit test arrangement. You can see easily understand secondary side is open circuit here. Okay, here you have the open circuit, and primary winding, that to LV. Primary is LV, secondary is HV. The test is always conducted from LV side. On LV side, we are using rated voltage as well as rated frequency. Voltage is rated value, frequency is also rated value. And in order to measure the voltage, we are using a voltmeter. To measure the current, we are using an ammeter. To measure the power, we are using wattmeter. Okay, and whatever wattmeter I am using here, this will measure the iron loss in the transformer. Okay, so why? Because secondary is open circuit, guys. Therefore, output power is equal to 0. For any system, what is the relation between input power and output power? We all know that input power is always equal to output power plus losses. But right now, output power is 0. Therefore, entire input power during open circuit test is just equal to losses. Losses are two types, right? What are those two? Iron loss and the second one, copper loss. We know copper loss is dependent on current or voltage. Current. There is no current on the secondary side. Secondary side current is 0. Primary side there is some current known as no load current. But we know no load current is very, very small. That's why we are neglecting copper loss. So if copper loss is neglected, then the entire input power during open circuit test is just equal to iron loss of the transformer. That is why I told you this test is used to measure iron loss in a transformer. And to measure this iron loss, we are using this wattmeter. Also, so the wattmeter will measure the iron loss. This ammeter will measure the no load current. Voltmeter will measure the rated voltage. Also, important observation is whatever wattmeter we are using in open circuit test, that means that is LPF type wattmeter. We are using, I think it is not visible, LPF type wattmeter. Why? Because we know the no load power factor of a transformer was very poor. What is the range of no load power factor? 0.2 to 0.3. I think I told you earlier. So as it is a poor power factor, we have to use LPF type wattmeter. In some textbooks, LPF type wattmeter is also written as ZPF type wattmeter. Anything is same. Okay. So this is open circuit test. Now how to calculate shunt branch parameters using this open circuit test? You remember I told you already during no load condition. Let me go back. Yes, here we discussed about equivalent circuit at no load. Can I say no load condition or open circuit condition both are same only? Yes. What is the formula for core loss resistance RC? RC is equal to V1 by IW, where IW is equal to I naught cos phi naught. XM is equal to V1 by I mu, where I mu is equal to I naught sin phi naught. And the same formulas I can use even in open circuit test also. Let us go. Yes. So for RC calculation, I can write what is the formula for RC? Yes. RC is equal to V1 by IW, where IW is equal to I naught cos phi naught. Okay, so here that V1 is nothing but voltmeter reading here. Okay, voltmeter reading means VOC. That I naught is ammeter reading, IOC. Therefore, the only unknown in this equation is the power factor cos phi naught. I'll tell you how to calculate. Next, coming to XM calculation, what is the XM formula? V1 by I mu, where I mu is equal to I naught sin phi naught. Okay, so here V1 is nothing but voltmeter reading, that is VOC. I naught is nothing but ammeter reading, IOC, and sin phi naught. So to calculate RC and XM, the only unknown values are cos phi naught and sin phi naught. Now remember, this cos phi naught is indirectly the power factor of the transformer at no load. I can find out that power factor using this wattmeter value. Because wattmeter will measure active power or reactive power? Active power. So we can write WOC is equal to VOC into IOC into cos phi naught. Because wattmeter will measure active power is simply VI cos phi. So from this we can write cos phi naught is equal to WOC by VOC into IOC. And definitely the power factor is lagging power factor because it is an RL circuit. So use cos phi naught and then you can find out both shunt branch parameters RC and XM, right? So this is open circuit test. Now let us understand short circuit test, the next one, important test. So first of all, what is the purpose of short circuit test? So short circuit test is used to determine rated copper loss of the transformer. Open circuit test is used to determine iron loss. Short circuit test is used to determine copper loss. We know copper loss is variable loss or constant loss, variable loss. And to measure rated copper loss, current must be rated value. Okay. Also, by using this test, series branch parameters can be identified. Open circuit test we found shunt branch parameters. Short circuit test we can find out series branch parameters. Also, during this test, high voltage winding is excited. That means the test is conducted from which side? High voltage side. Whereas open circuit test we will conduct from low voltage side, but short circuit test we will conduct from high voltage side. Important. Yes, if high voltage side is excited, which side is short circuited? Low voltage side is short circuited. Now you can see this arrangement here. See, high voltage side is the primary where excitation was given. Low voltage side is the secondary where the short circuit was happened. And remember guys, as the secondary was short circuited, a small voltage is sufficient to circulate rated current. Okay, when a secondary is short circuited, a small voltage will be sufficient to circulate rated current, guys. Why current must be rated value? If a current is rated value, then only copper loss will be rated value, because the purpose of this test is to determine copper loss. Copper loss will depend upon current. So to circulate rated current, short circuit the secondary side. Whenever there is a short circuit, we know a small voltage will be sufficient to circulate rated current. And you can measure that rated current using this ammeter. This ammeter will measure the rated current. This voltmeter will measure the small voltage that we are applying. And this wattmeter will measure the copper loss. Alright, copper loss. And this time you don't need to use LPF type wattmeters. We will use HPF type wattmeters, because short circuit power factor is more than 0.5. Okay, short circuit power factor is generally 0.5 to 0.6 lagging. As the power factor was more than 0.5, we will use HPF type wattmeter. Okay. So in open circuit test, we used LPF type wattmeter. In a short circuit test, we will use HPF type wattmeters. Now the point is how to find out the series branch parameters. First, let us draw the equivalent circuit. Remember, all meters are on primary side or secondary side? Primary side. Therefore, whatever parameters we are finding, they are all referred to primary. Primary means HV. Okay. So first draw the circuit diagram. Yes. During a short circuit, only series branch parameters will be available. That is the total resistance referred to primary, total leakage reactance referred to primary, and then the circuit is a short circuit. That's all, simple circuit. Only series branch will be available. Shunt branch can be neglected during a short circuit test. Why? Because voltage was very small. And that small voltage, we are calling it as VSC. And the rated current, we call it as ISC. Now, I can combine this resistance and reactance together as an impedance Z01. So, if you apply KVL equation, what happens? VSC is equal to ISC into Z01. From this, what is Z01 is equal to VSC by ISC. Can I say the unit for impedance is ohm? Yes. VSC by ISC is equal to Z01. Now the point is how to find out resistance and reactance separately. Yes, very simple. In a series impedance, real part is nothing but cos term of the impedance. Imaginary part is nothing but sine term of the impedance. Therefore, R01 is simply Z01 cos phi SC, because it is short circuit test. X01 is equal to Z01 into sine phi SC O. Now the doubt is, how do you know that cos phi SC and sine phi SC? That is where wattmeter reading will help you. Wattmeter will generally measure active power or reactive power. Active power. Active power is nothing but VI cos phi. So from this we can find out cos phi. Therefore cos phi is equal to active power divided by voltage into current lagging. Okay, so this is how do you calculate series branch parameters using short circuit test. And there will be two important formulas we have to remember from short circuit test. I am not doing the derivation, I will directly write down. Yes, one formula is Z per unit formula. Z per unit is equal to VSC by V-rated. We all know during a short circuit test we are using a rated voltage or very small voltage. Yes, that very small voltage divided by rated voltage will give you per unit impedance. Okay, and there is one more formula known as steady state short circuit current. Steady state short circuit current is equal to 1 by Z per unit times of rated current. Okay, this steady state short circuit current is also known as fault current of the transformer. Okay, and fault current of the transformer is equal to 1 by Z per unit times of rated current. Clear? Okay. Now we will try to answer one question related to the testing on a transformer. This is a question in GATE 2008 exam. Just read the problem. It is desired to measure parameters of 230 volt by 115 volt 2 kVA single phase transformer. The following wattmeters are available in a laboratory. You see 4 wattmeters are available. Every wattmeter voltage rating, current rating and power factors are given. The wattmeters used in open circuit test and short circuit test will be respectively what? Which wattmeters we will use for open circuit test and which wattmeter we will use for short circuit test is the discussion. Let us talk about open circuit test first. We know open circuit test means voltage is rated value, correct? I better write like this. Yes, during a short circuit test, voltage is rated value, current is negligible value because no load current is very small. Also, what is the type of power factor? LPF type wattmeters are preferred, right or not? Because power factor is very poor. And one more thing, OC test is preferable to conduct from LV side or HV side? LV side. Test is conducted from LV side. Therefore, if you come back to the question, what are the only wattmeters with low power factor? Yes, W1 and W2. W3, W4, I can't use for OC test. Why? Because they are high power factor type. So you need to decide between W1 and W2 where I need to check voltage rating. Current rating I need not to check. Why? Because current is negligible during OC test. And the test is conducted from which side? LV side. Let us go back to the transformer. LV side, what is the voltage? 115. That means the wattmeter should be able to withstand at least 115 volt. But here both W1 and W2 can withstand up to 250. When I say wattmeter can withstand up to 250, they can easily withstand 115, right? That is why for OC test you can use either W1 or W2. W1 or W2. You can use any wattmeter. Why? Because both can withstand 115 volt. Why I am not talking about current rating? Why? Because current is negligible during OC test. Now let's talk about short circuit test. Yes, short circuit test is performed on which side of the transformer? HV side. Next, during a short circuit test, voltage is very small, neglected, but current is rated value and power factor is high power factor. High power factor means which wattmeters are available? Yes, now you cannot use W1 and W2. We have to check W3 and W4. Why? Because W3, W4 has high power factors. W1, W2 I can't use for SC test. But as I mentioned, during SC test, current is rated value, guys. Voltage is negligible. So let us calculate the rated current of the transformer, that too on HV side. If I go back to the ratings of the transformer, you see 230 volt by 115 volt 2 kVA. It was 230 volt by 115 volt 2 kVA transformer. Now let us check the rated current on HV side. So what is the formula for rated current? Very simple. Rated current means VA rating divided by voltage rating. Correct or not? What is the VA rating of the transformer? 2 kVA, that is 2000 divided by what is the rated voltage? I must use 230 or 115. 230, why? Because I have to calculate rated current referred to HV side. Now if I complete this calculation, 2000 by 230, let me calculate. Yes, 8.69 ampere. That means what? The wattmeter should be able to withstand at least 8.69 ampere. But if I go back, wattmeter 3 can withstand up to 10 ampere. That means it can easily withstand 8.69 ampere. But wattmeter 4 can withstand only 5 ampere, but transformer current is 8.69. Therefore, this wattmeter gets overloaded. Okay, that means which wattmeter is suitable for SC test? W3 only. Okay, therefore W3 is only suitable for SC test. Why I am not talking about voltage ratings of these two wattmeters? Why? Because during SC test, voltage was very small, we can almost neglect it. That means voltage rating doesn't matter for the wattmeter, current rating matters. So finally, what are the conclusions? For OC test, you can use either W1 or W2, but for SC test, you can use only W3. Therefore, last option will be suitable. For SC test, only W3, but for OC test, either W1 or W2. Therefore, the suitable option will be the last one. Okay, so simple question. Just a moment, guys. All right, now let's move to our next discussion, that is efficiency calculations in transformer. Okay, efficiency is one of the important performance parameter in transformer. We must design transformers to have higher efficiency always. But there are two types of efficiencies we will generally study in transformers. One is power efficiency, another one is energy efficiency. Okay, energy efficiency is also known as all-day efficiency of the transformer. Okay, all right. So what is the formula for power efficiency? It's a general formula. It is the ratio between output power to input power, and it can be expressed in per unit or percentage. To express in percentage, we have to multiply with 100. And again, input power can be written as output power plus losses. Now you take output power common in numerator and denominator and cancel it. Then what is the final equation? 1 by 1 plus losses by output power. So according to this equation, if I want maximum efficiency from a transformer, can I say this denominator must be minimum? I can say this denominator is minimum only when this ratio is minimum. What is this ratio? Losses to output power ratio. So a transformer, a given transformer will offer maximum efficiency when losses to output power ratio is minimum. All right. Okay. Fine. Now, that is the word I wrote here very clearly. Maximum efficiency is possible at a load where losses to output power ratio is minimum. Now we will try to understand the equation for various efficiency values. Okay, that is efficiency at full load, efficiency at half load. Okay, like that. So as I told you, what is the formula for efficiency? Output power by output power plus losses. Okay, that to active power I have to use. Active power means, can I say VI cos phi, that is VA rating of the transformer into power factor of the load cos phi, divided by VA rating into power factor plus losses means there are two types of losses. Iron loss is there and full load copper loss is also there. And if you multiply with 100, you will get percentage efficiency. And most importantly, this is the efficiency at a full load, guys. Efficiency at full load. Okay. Suppose if it is at half load, let us say, half load means, yes, you need to multiply that VA rating with 0.5. Okay. So let me change the color. Yes, if it is half load, that VA rating must be multiplied with 0.5. Okay, you have to multiply the VA rating with 0.5. Even here also, Because half load means voltage becomes half or current becomes half. Current becomes half. When current becomes half, the volt ampere power also becomes half. Therefore, we need to multiply with 0.5. But iron loss, you need not to multiply with anything. Why? Because iron loss is a constant loss. But copper loss is subjected to change. What is the copper loss at half load? 0.5 square times of full load copper loss. Similarly, what is the efficiency at X percentage load? You multiply the VA rating with X, where X represents the per unit load, guys. If it is a full load, X equal to 1, half load 0.5, 90% load 0.9, and copper loss you must multiply with X square. Copper loss at X percentage load is X square times of full load copper loss. But one thing you need to understand, iron loss doesn't change. Whether it is a full load or half load or any random load, iron loss doesn't change. Why? Because iron loss belongs to a constant loss. This is general formula for efficiency at different loading conditions. And suppose you see all the values that I mentioned in this entire formula, they are actual values. That means this loss is in watt, actual power loss. Okay, that is in watt. Similarly, this is also watt. Okay, actual values. Suppose if the question has per unit values instead of actual values, then what you do is that take VA rating common in numerator and denominator and cancel it. Then you will get efficiency equation in per unit values. Then you see the numerator X into VA rating cos phi 2 will become X into cos phi 2. And the denominator also, this is now per unit iron loss. This is per unit full load copper loss. So you can use any formula. This is the formula when all values are in actual values. This is the formula when all values are expressed in per unit values. Okay, any formula we can use, all right, based on the available data in the question. Now, if you look at the last formula carefully, yes, efficiency of a transformer will depend upon two important parameters. One is load power factor, that is cos phi 2. Another one is percentage load, that is X value, full load, half load, quarter load, like that. Okay, so these two parameters will affect the percentage efficiency of a given transformer. Therefore, using these two parameters, we will try to understand what is the condition for maximum efficiency of a transformer. Now you see that first observation, everything will have a derivation. I am not discussing derivations right now. Directly we are writing the important points. Yes, maximum efficiency can be obtained at unity power factor load. Unity power factor means resistive load. If the load is unity power factor type, then efficiency will be maximum. You can see this curve. If I take efficiency on y-axis and power factor on x-axis, highest efficiency is possible at which power factor? Unity power factor. If a power factor reduces, efficiency will also reduce. If a power factor increases, efficiency will also increase. Okay. Similarly, this is with respect to load power factor. What about with respect to load? So with respect to load, maximum efficiency can be obtained at a load where X is equal to square root of iron loss by full load copper loss. This is the most important formula from entire efficiency topic. Okay, what is X here? X is the load where efficiency is a maximum value. The load where efficiency is maximum value. Suppose if you perform this calculation and you got X equal to 0.8, what is the meaning of it? Maximum efficiency can be obtained at 80% load. Suppose you perform this calculation, you got X equal to 1, let us say. What is that meaning? Maximum efficiency can be obtained at full load. That is the meaning of it. So X will represent the percentage load at which maximum efficiency can be obtained. Okay, and you can see what is the performance of efficiency with respect to load. You can see here, this is the point where maximum efficiency can be obtained. That is the point where copper losses are equal to iron losses. X equal to square root of iron loss by full load copper loss. Let us say maximum efficiency is 95% for a given transformer, just a random value. If maximum efficiency is 95%, you take another efficiency, let's say 90%, which is less than maximum value. Can I say this 90% efficiency I can get at a loading equal to x1? At x1 loading, efficiency is 90%. And I can get the same 90% efficiency at one more loading x2. Therefore, in a transformer, it is possible to get same efficiency at two different loading guys. But maximum efficiency we can obtain only at one loading, that is where x equal to square root of iron loss by full load copper loss. Got it? Yes, this is the condition for maximum efficiency of a transformer. And what is the formula for maximum efficiency? Important thing is, at maximum efficiency, the variable loss will be equal to constant loss. Okay, that means copper loss value is equal to iron loss. Therefore, what is the total loss at maximum efficiency? Total loss at maximum efficiency is equal to 2 times of iron loss. Remember, maximum efficiency means copper loss becomes equal to iron loss, or iron loss becomes equal to copper loss. Yes, copper loss becomes equal to iron loss. Copper loss is the variable value. Whenever load changes, copper loss will change. But at one particular load, that copper loss will be equal to iron loss. That is where efficiency will be maximum. And at maximum efficiency, what is the total loss in the transformer? The total loss in the transformer will be equal to 2 times of iron loss. Therefore, this is the formula for maximum efficiency. Okay, actually it is equal to, and here I must multiply with 100. So x into cos phi 2 by x into cos phi 2 plus, this is important. The total loss is equal to 2 times of iron loss. Just a moment. The total loss is equal to 2 times of iron loss. Clear? Okay, so this is the point I mentioned very clearly. At maximum efficiency, the total power loss is equal to 2 times of iron loss. Clear? Okay. Now this is maximum possible efficiency, guys. What is the difference between maximum efficiency and maximum possible efficiency? See, this is the maximum efficiency at a given power factor. Suppose I ask you, find out maximum efficiency at 0.8 power factor. This is the formula. But I ask you to find out what is the maximum possible efficiency, then this is the formula. Maximum possible efficiency means two conditions I have to implement. One is maximum efficiency with respect to power factor, maximum efficiency with respect to loading. As I studied already, maximum efficiency can be obtained at unity power factor. Therefore, in this maximum efficiency formula, you just replace power factor as unity. Then this is highest possible efficiency from the given transformer. That means you can't get more than this efficiency. That is the meaning of it. Okay? Yes. Fine. Now next one, energy efficiency. It's not so important, but understand, energy is nothing but power multiplied by time. You get a power means VA cos phi, and you multiply that with time in hours. And how many hours we will take? 24 hours calculation. That is why we call it as all day efficiency. One particular day time we will take approximately 24 hours. And within that 24 hours, how much energy is delivered with respect to the energy drawn from the source is nothing but energy efficiency. Okay, fine. Now we will try to answer one question related to these efficiency calculations. Just read the problem. The percentage resistance and percentage reactance of a 10 kVA 400 volt by 200 volt 3-phase transformer are 2% and 10% respectively. If the constant losses in the machine are 1%, what is the maximum possible percentage efficiency of the transformer? So we are asked to calculate maximum possible efficiency. For that purpose, percentage resistance is given. What is the percentage resistance? Yes, percentage resistance was 2%. Okay. That means what is the per unit resistance? That is 0.02. We know per unit resistance is nothing but a full load copper loss value of the transformer. Yes, this is nothing but full load copper loss in per unit value. Okay. Next, iron losses are already given because we know constant losses are nothing but iron losses only. Yes. Already it is given iron losses are equal to 1%. That means 0.01 per unit. Therefore, find out condition for maximum efficiency. Therefore, condition for maximum efficiency. Yes, we can obtain maximum efficiency at a load X is equal to square root of iron loss divided by full load copper loss. So, square root of what is iron loss? 0.01 by full load copper loss 0.02. This will give you the condition for maximum efficiency. So, let me do the calculation. So 0.707. Therefore, maximum efficiency can be obtained at a load where X equal to 0.707. But we are simply asked to identify maximum efficiency or maximum possible efficiency. Maximum possible efficiency. We know maximum possible efficiency means what is a power factor? Unity power factor, right? This is the formula I already mentioned. So can I substitute directly here? X is equal to 0.707 divided by 0.707 plus 2 times of iron losses. Iron loss is 1%. Therefore, this is the maximum possible efficiency. Okay, so let me calculate. Yes, 97.24%. 97.24% is the maximum possible efficiency. Okay, so I think option B is the correct answer. Very simple question. It is given for 2 marks. Suppose if I may change this question, I may ask you what is the maximum efficiency at 0.8 power factor? Then you have to use this formula. This is the maximum efficiency at a given power factor. X into cos phi 2 by X into cos phi 2 plus 2 times of iron loss. Okay. Yes. Clear? Fine. Now let's discuss about the last topic of single phase transformers, that is voltage regulation in a simple detailed manner. Okay. Fine. So let's see voltage regulation now. This is the last topic in our single phase transformers. Okay, so first of all, what is the definition for voltage regulation? It is another performance parameter of a single phase transformer, and regulation should be as low as possible. First of all, what is the definition? Voltage regulation is defined as the change in terminal voltage from no load to full load. From no load to full load, what was the change in the terminal voltage? Terminal voltage means this V2. Okay, that is what we call it as voltage regulation. I can calculate it from from the equivalent circuit, but remember I have drawn the equivalent circuit referring all parameters to secondary side, because generally we will calculate the voltage regulation on the load side. That is why no load to full load is the word we used. And there is no shunt branch. That means during voltage regulation calculations, no load current I0 will be neglected. Okay. Fine. Now let us see what is a formula for voltage regulation. Voltage regulation is simply the change in terminal voltage from no load to full load. So voltage regulation is equal to no load terminal voltage minus full load terminal voltage. No load terminal voltage means this value E2, because when the load is disconnected, no drop in this impedance, so terminal voltage is simply E2, minus full load terminal voltage is V2. So voltage regulation is E2 minus V2. And if I apply KVL equation, how to write KVL equation in this loop? Yes, E2 is equal to V2 plus the current I2 into impedance Z02. But remember, vectorially we have to add, that is very, very important. And here I gave you clearly what are the formulas for voltage regulation for lagging power factor as well as leading power factor. See, Same formula, same KVL equation. We will take this terminal voltage as reference. Terminal voltage is reference. So V2 is at an angle 0. Coming to current I2, the angle is very important. If it is lagging power factor angle, I2 will be at an angle minus phi, where phi is the power factor angle. And impedance is nothing but, can I say, resistance plus reactance? That's all. And suppose if it is leading power factor load, the only change is the current will be now at a positive angle. Okay, because we know leading power factor means current will lead the voltage, positive angle. Lagging power factor lags the voltage, so negative angle. But the disadvantage of this KVL equation is complex calculations. But you are writing an exam where the GATE calculator do not have complex mode. That's why I suggest to avoid these calculations. These calculations you can use if a problem is simple. Also, if you have a proper calculator with you. But if you wanted to make it simple with normal GATE calculator, yes, this is the formula that we are going to use. E2 minus V2 is equal to I2 R0 to cos phi 2 plus or minus I2 X0 to sin phi 2. Actually, this is a formula derived from a phasor diagram of transformer. The derivation we are not doing. Final formula I have represented here. So I2 R0 to cos phi 2 plus or minus I2 X0 to sin phi 2. And when should we use a positive sign? Positive sign we have to use when it is lagging power factor load. Minus sign we have to use when it is leading power factor load. And the unit for voltage regulation was volt. That means it is actual value of voltage regulation. And you can also express per unit voltage regulation. That is the ratio from actual voltage regulation to base voltage. And the formula, very important formula, per unit voltage regulation is equal to R per unit cos phi 2 plus or minus X per unit sin phi 2. Where cos phi 2 is nothing but a load power factor. If you know load power factor cos phi 2, you can immediately calculate what is sin phi 2 as well. Once again, plus is the sign we have to use when the load is lagging power factor type. Minus is the sign you have to use when the load is a leading power factor type. Okay. Whereas R per unit and X per unit are transformer resistance and reactance in per unit values. You can also calculate percentage voltage regulation. Percentage regulation means you just multiply per unit voltage regulation with 100. So that is a percentage resistance cos phi 2 plus or minus percentage reactance sin phi 2. Okay. Yes. Now, two important conditions we have to study in voltage regulation. That is condition for zero voltage regulation and condition for maximum voltage regulation. Yes. Important thing is zero voltage regulation is possible only for leading power factor load. Only when the power factor of the load is leading, then zero voltage regulation can be obtained. What is mean by zero regulation? Regulation means the change in voltage. Zero regulation means no change in voltage. No change in voltage means, can I say voltage is a constant value from no load to full load? Yes, then only I must call it as zero voltage regulation. Yes, zero voltage regulation is possible only for a leading power factor load. And what is the formula? Yes, zero voltage regulation is possible at a power factor cos phi 2 is equal to X per unit by Z per unit. Most importantly, this is leading power factor. At this leading power factor, voltage regulation will be zero. Similarly, what is the condition for maximum voltage regulation? Yes, maximum voltage regulation is possible only for a lagging power factor load. Remember, not all the lagging power factor loads, a particular lagging power factor loads. And what is the formula? Yes, lagging power factor cos phi 2 is equal to R per unit by Z per unit. R per unit by Z per unit, or R02 by Z02. Important thing is this is lagging. Okay, lagging power factor. Okay, so maximum regulation, zero regulation is possible at X by Z. We know that X by Z means I can continue this. See, one second. Yes, cos phi 2 is equal to X by Z. Can I write Z is equal to square root of R square plus X square? We know generally winding resistance is very low or reactance is very low? Resistance is very low compared to reactance. Therefore, this ratio is very near to 1. Generally, 0.9 to 0.95 leading. So, zero voltage regulation is possible for a leading power factor load very near to unity. Whereas, maximum voltage regulation, you see the power factor, at what power factor it is happening? R by Z. R by Z means R square plus X square. Important thing is R is very small. When I say R is very small, can I say this ratio is very near to 0? So maybe 0.1 to 0.2 lagging. So zero voltage regulation is possible for a power factor near to unity on the leading side. Maximum voltage regulation is possible for a power factor which is near to 0 on the lagging side. Okay? And then magnitude of the maximum regulation. When I say regulation is maximum, how much is its magnitude? Yes, maximum voltage regulation magnitude is equal to percentage impedance of the transformer. Remember, percentage impedance you can calculate from short circuit test. You remember the formula? In short circuit test, I told you Z per unit is equal to VSC by V rated. So by using a short circuit test, you can find out per unit impedance, and that per unit impedance is nothing but maximum voltage regulation of the transformer. And this is how regulation curve can be obtained. Remember, this curve is valid even for alternator also. Even for alternator also, voltage regulation curve will be same. See, this is a maximum regulation. Maximum regulation is possible on the lagging power factor side near to 0. This is zero regulation. Okay? Zero regulation is possible on the leading power factor side near to unity. See, very near to unity. Okay? This is voltage regulation curve of a transformer. Now we will find one simple problem related to voltage regulation. This is a question in GATE 1999. Read the problem. A 10 kVA 400 by 200 volt single phase transformer with percentage resistance of 3%. See, resistance is 3%. And percentage reactance of 6% is supplying a current of 50 ampere to a resistive load. 50 ampere to a resistive load. What is the value of load voltage is the question. Okay. So first, if you read the problem, percentage resistance was given 3, percentage reactance was given 6, load current was given 50 ampere, and what is the type of the load? Resistive load means, can I say power factor of the load is unity? Now my first question is, will this 50 amperes is rated current or not? Let us check. Then only I can apply regulation formula. First of all, look at the rating of the transformer. Yes, it was 10 kVA 400 by 200 volt. Yes, who is a secondary? Obviously 200, secondary side voltage. Therefore, calculate secondary side rated current. Always remember, rated current is equal to VA rating by voltage rating. So, VA rating was 10 kVA, that is 10 into 10 power 3 by voltage 200. Therefore, rated current was 50 ampere. Rated current was 50 ampere, but right now the load current is also 50 ampere. That means transformer is at full load. If I say transformer is at full load, all our regulation formulas are valid here. What is the formula for percentage voltage regulation? Percentage voltage regulation is equal to percentage R cos phi 2 plus or minus percentage X sin phi 2. Right now, what is cos phi 2? 1, because unity power factor. What is percentage R? 3%. 3 into unity. And remember, sin phi 2 is 0. Yes, because cos phi 2 1 means sin phi 2 0. Therefore, percentage voltage regulation is equal to 3%. What is the formula for percentage voltage regulation? Can I say E2 minus V2 by E2 into 100 is equal to 3. So E2 is how much? E2 is 200. So 200 minus V2 by 200 into 100 is equal to 3. So I think from this you can calculate what is V2 value. Okay. So let us calculate what is V2. I think 194 is the correct answer. Correct? Yes. Therefore, the terminal voltage of the transformer with respect to the resistive load is 194. Okay. Yes. Simple question. Most important thing is all the formulas that we derived here, this this voltage regulation formula, R per unit, cos phi to X per unit, these are all formulas valid for full load. At full load. Suppose if you want voltage regulation at half load, you multiply 0.5. Why? Because you see this formula, you can take I2 common here, right? Therefore, voltage regulation is directly proportional to current. That means if you know full load regulation, then at X percentage load, regulation will be X times of full load regulation. That is why whenever problem was given related to voltage regulation, the first thing you need to do is that compare the load current with rated current of the transformer. Fortunately here, load current and rated current both are same. That means a transformer is at full load. That's why I'm directly using this formula. Suppose, let us say rather than 50, I gave you 25 ampere only here. Then what happens? That means can I say load current is only half of the rated current? As load current is only half of the rated current, voltage regulation formula, you just multiply this formula with 0.5. Because I need to use only half load voltage regulation. Got it? So, if it is a full load regulation, then only this formula is valid. If it is at half load or some other load, you have to multiply with that X value. Clear? That's all. This is about voltage regulation in the transformer. Okay? Alright. So, with this, I think single phase transformers concepts have been completed. Okay? I tried to discuss the concepts in a very crisp manner. Okay? Only important points we discussed. It's a subject I use it to discuss for 45 hours in classroom. So we tried to cover the single phase transformers in a very short period of time, mentioning the important points. Also we solved example questions related to every topic, and I request all of you please practice all previous GATE examination questions. In our YouTube channel already transformers previous year questions were added. You can search them and you can watch those videos. Okay, so that you can understand how to solve each previous year question. Okay, so now it's time for your questions. Okay, so I'll be going to the chat box. Okay, in the charts, I will try to give you the reply related to the questions that you are giving. Okay, yes. Keep posting your questions. So I'll try to give you reply. Okay, now let's try to look at some of the queries raised by the viewers. Yes, so there are so many messages. So as I'm during the lecture, I was unable to see all your messages. So, but now I was able to see your messages. Okay, I didn't find any doubts. There are more generalized questions are there. Yes. Yes, one question, sir, can we give the current source directly to the transformer? See, first of all, there is nothing like current source in practice. Okay. So generally you connect a voltage source in series with a large inductance, that itself is acting like a current source. Okay. So current source is a generalized form, or you can say it's a modeling of a voltage source in series with a large inductance. Okay. So that is what. Yes, you can give current directly to transformer, no problem at all. In fact, at no load condition, you don't give current to transformer. Actually, current was drawn by the transformer. Okay. So that is what we need to understand. Okay. Any more questions, please let me know in the chat section so that I will try to answer the questions. Yes, a single phase induction machines, yes, I will deal that, no problem. Okay, in this champion series, I'll discuss all electrical machines one by one. So in the next series, I'll take up 3-phase transformers. then another machine. Okay, each machine I will divide into two parts and we'll discuss. Yes, very good evening. Actually, I couldn't see your messages initially. Yes, any more questions? Okay, then. So I think there are not many doubts further. Okay, so we will conclude the session here today, and yes, sure. We will discuss third harmonic neutralization. I will discuss in three-phase transformers itself. Effect of magnetic nonlinearity. Okay, that will come in three-phase transformers. Both single phase and three phase together I will discuss there. Okay. All right. Okay then guys. So go through our YouTube channel. You can go to playlist and there is a section called electrical machines. I discussed all previous gate questions earlier. So you can watch those videos and you try to practice single phase transformers previous gate questions. Okay. So what will happen if we give DC to transformer? Yes, see, generally you look at the equivalent circuit of a transformer. We have a resistance in series and also there is a reactance in shunt, right? So when you give DC supply to transformer, what happens? The reactance will be short circuited. So the transformer will offer only resistance, okay? And the resistance of transformer is generally very low. Therefore, if you give a very high DC voltage, then a large current will circulate through transformer because only resistance will be available in the transformer winding. And we design transformer winding to have very low resistance, right? Therefore, a very large current will circulate. Of course, it depends upon the supply voltage that you are giving. If you give large voltage, then more current will circulate. That more current may overheat a transformer winding. So there is a chance that a transformer winding may damage. But you can give small DC voltage, no problem. That is where we call the transformer as pulse transformers. So you study pulse transformers. Pulse transformers are used to give triggering signals for thyristors in power electronic circuits. That is where we will give small DC pulse, right? We will give DC supply as input, but a very small voltage we will give. But it is not a continuous DC. We will give in terms of pulses. Okay, yes, you can give DC to transformers, but how much DC we are giving is important. Yes, R per unit can be equal to full load copper loss by VA rating. That is a derivation. You have to practice that derivation. So in this quick review session, I can't perform all the derivations, right? Okay. So you can write the formula, right? Full load copper loss by VA rating. Full load copper loss means I square into R divided by VA rating means V into I. So I square into R divided by V into I. One I will cancel. You take the remaining I to the denominator. Then it will become R by V by I. V by I is base impedance. So R by base impedance is nothing but per unit resistance. Okay. You can easily perform the derivation. All right. Anything more? Okay then, so we'll meet in one more session very soon about three-phase transformers. So till then, thank you so much. Have a nice day. Okay, bye-bye.